Today, I'll be talking to Evan Hubinger about risks from learned optimization. Evan is a research fellow at the Machine Intelligence Research Institute, was previously an intern at OpenAI, working on theoretical AI safety research with Paul Cristiano. He's done software engineering work at Google, Yelp, and Ripple, and also designed the functional programming language Coconut. We're going to be talking about the paper Risks from Learned Optimization in Advanced Machine Learning Systems. The authors are Evan Hubinger, Chris van Merwijk, Vladimir Miklik, Jor Skalse, and Scott Garbrand. So, Evan, welcome to Excerpt.
Thank you for having me, Daniel.
Yeah, so the first thing I wanted to say about this paper is it has a nice a glossary at the end with like what various terms mean, and I think this is like sort of unusual in machine learning papers. Just straight off the bat, I wanted to firstly thank you for that and let potential readers of the paper know that it's maybe easier to read than they might think.
Yeah, thank you. Yeah, we worked hard on that. I think one of the things that we sort of set out to do in the paper was define a lot of things and create a lot of terminology. And so in creating a lot of terminology, it's useful to have a reference for that terminology. And so we figured that would be helpful for people trying to go back and look at all of the terms that we're using. In terms of evolve over time, it's not necessarily the case that the same terms that we use in our paper are going to be used in the future, or people might use them differently. But we wanted to have like a clear reference for, we're going to use a lot of words. Here are the words, like here's what they mean, here's how we're defining them, here's how we're using them. So at least if you're looking at the paper, you can like read it in context and understand what it's saying and what the terms mean and everything.
Yeah, that makes sense. Just a heads up for this, for the listeners. In this episode, I'm mostly going to be asking you questions about the paper rather than walking through the paper. That being said, just to start off with, I was wondering if you could briefly summarize, like, what's the paper about and what's it trying to do?
Yeah, for sure. So essentially, the paper is looking at trying to understand what happens when you train a machine learning system and you get some model. And that model is itself doing optimization. It is itself trying to do some search. It's trying to accomplish some objective. And it's really important to distinguish between, and this is sort of one of the main distinctions that the paper sort of tries to draw, is the distinction between the loss function that you train your model on and the actual objective that your model learns to sort of try to follow internally. And so we make a bunch of distinctions. We try to sort of define these terms, where specifically we talk about these sorts of two alignment problems. The outer alignment problem, which is the problem of aligning the sort of human goals, the thing you're trying to get it to do, with the loss function. And the inner alignment problem, which is how do you align the actual objective that your model might end up pursuing with the loss function. And we call this sort of actual objective the MESA objective. And we call a sort of model, which is itself doing optimization, a MESA optimizer.
What's MESA, by the way?
Yes, that's a very good question. So MESA is Greek. It's prefix, and it's sort of the opposite of meta. So meta is Greek for sort of above. MESA is sort of Greek for below. The idea is that if you could think about sort of meta optimization in the context of machine learning, meta optimization is when I have some sort of optimizer, a gradient descent process, sort of training process or whatever, and I create another optimizer above that optimizer, a meta optimizer to sort of optimize over it. And we want to sort of look at the opposite of this. We want to look at the situation in which I have a training process, I have a sort of loss function, I have this sort of gradient descent process. What happens when that gradient descent process itself sort of becomes a meta optimizer? What happens when the thing which it is optimizing over, the model, the actual sort of trained neural network, itself develops an optimization procedure? And so we want to call that MESA optimization, for it's sort of the opposite of meta optimization. Instead of having optimization one level above what we're sort of expecting, we have optimization one level below.
Cool. So one question I have about this paper is, like, you're thinking about optimization. Like, where's optimization happening? What's it doing? What's optimization?
Yeah, so that's a great question. And I think this is one of the sorts of things that it's notoriously difficult to define. And there's a lot of sort of definitions that have existed out there, different people trying to define it in different ways. You have things like, Daniel Dennett's like intentional stance. You have things like Alex Flint recently had a sort of post on the alignment forum going into this. In risk-learned optimization, we sort of define optimization in a very sort of mechanistic way, where we're like, look, a system is an optimizer if it is internally doing some sort of search according to some objective, searching through a space of possible plans, strategies, policies, actions, whatever. And the argument for this is, well, once you have a model which is doing search, It has some large space of things, and it's trying to look over those things and select them according to some criterion. That criterion has become an objective of sorts, because now it is selecting the way in which its output is produced has a large amount of sort of optimization power, a large amount of sort of selection going into choosing which things satisfy this criterion. And so we really want it to be the case that whatever that criterion that exists there is one that that we like. And furthermore, it's the sort of thing which we argue is you should actually expect that you will learn models which have this sort of search, because search generalizes really well. It's a relatively simple procedure. And then finally, also, search having this sort of mechanistic definition lets us sort of make a lot of arguments and sort of get to a point where we can understand things in a way where if we just adopted a sort of behavioral definition, like the intentional stance, for example, we wouldn't be able to do. Because we want to be able to say things like, how likely is it that when I run a machine learning process, when I do a training process, I will end up with a model that is sort of an optimizer? And it's very difficult to say that if you don't know what an optimizer looks like internally. Because I can say, well, how likely is it that I'll get something which is well described as an optimizer? And that's a much more difficult question to answer, because you don't know sort of, the process of gradient descent, the process of machine learning, it selects on the internals, it selects on, we have all of these sort of implicit inductive biases, which might be pushing you in one direction. And then you have this sort of loss function, which is trying to ensure that the behavior of the model has, particular properties. And to be able to answer whether or not those inductive biases are going to push you in one direction or another, you need to know things like how simple is the thing which you're looking for according to those inductive biases. How likely is it that the process of gradient descent is going to end up in a situation where you end up with something that satisfies that? And I think the sort of point where we ended up was not that there's something wrong necessarily with the sort of behavioral stance of optimization, but just that it's very difficult to actually understand from a concrete perspective the extent to which you will get optimizers when you do machine learning if you're only thinking of optimizers behaviorally, because you don't really know to what extent those optimizers will be simple. Well, to what extent will they be favored by gradient descent and those inductive biases and stuff. And so by having mechanistic definition, we can actually sort of investigate those questions in a much more concrete way.
So one thing that strikes me there is if I were thinking about what's easiest to learn about what neural networks will be produced by gradient descent, I would think gradient descent, it's mostly selecting on behavior, right? It's okay, how can I tweak this neural network to produce behavior that's more like what I want, or outputs, or whatever is appropriate to the relevant problem. And famously, we currently can't say very much about how the internals of neural networks work. Hopefully that's changing, but not that much.
Absolutely.
So it strikes me that it might actually be easier to say behaviorally, we're going to get things to behave to optimize an objective function, because that's the thing that is optimal for the objective function. So I was wondering, it seems in your response, you put a lot of weight on networks will select simple, or optimization will select simple networks or simple algorithms, and I'm wondering why do you have that kind of emphasis instead of the emphasis on selecting for behavior?
Yeah, so that's a really good question. So I think the answer to this comes from, so first of all, let me just establish, I totally agree. And I think that it's in fact a problem that the way in which we currently do machine learning is so focused on behavioral incentives. One of the things that in my research, I actually sort of have spent a lot of time looking into and trying to sort of figure out is how we can properly do mechanistic incentives. How can we create ways to train neural networks that are focused on making them more transparent, or making them, able to sort of be, satisfy some sort of internal properties we might want. That being said, the reason that you can't, I think it's very difficult to sort of analyze this question behaviorally is because fundamentally, we're looking at a problem of unidentifiability. If you only look at behavior, you can't distinguish between the model, which is internally doing some optimization process, it has some objective and produces the sort of particular results, versus a sort of model which doesn't have any sort of internal objective. It's just sort of produces the same, but it still produces the same results on the training process, just has a bunch of heuristics. But those two models have very different generalization behavior. And it's the generalization behavior that we care about. We're looking for situations in which, and we sort of talked about this a little bit. There's this post by Vlad that sort of talks about this sort of 2D robustness picture, where the thing that we're fundamentally concerned about is a situation where you have a model, and the model is very robust in the sense of sort of competitiveness. This sort of it's very sort of capability robust. It has the ability to pursue whatever objective it is pursuing very effectively off distribution and on distribution. But it's not very objective robust. So it learned some sort of proxy objective maybe that works sort of pretty well on the training distribution, but doesn't work very well off distribution. And the problem is that if you're just looking at the behavior on the training distribution, you can't really distinguish between a model which like will be objective robust, which like has learned a proxy which like will work well off distribution, and a model which has learned a proxy which won't work well off distribution. Because if you're just looking at the training distribution and you're just looking at its behavior on the training distribution, you can't tell because those might just look identical on the training distribution. As a really concrete example, this sort of maze example that I often like to give. So you have a situation where I'm training a model on the training distribution has a bunch of sort of mazes, and I want it to get to end of the maze. And I put a little green arrow at the end of the maze, and I incentivize the model for getting to the end. And I train a bunch of these sort of relatively small mazes. And then I deploy the model in a new situation where I have larger mazes, and I put the green arrow at some random place in the middle. And now there's a bunch of things that can happen. So it could be the case that in this sort of new deployment environment, the model is sort of capability robust and it really knows how to solve mazes. But it can also not be capability robust and it just can't solve the bigger mazes. But if it is capability robust, then there's sort of two options. It's either objective robust and it learned the correct proxy, which was getting to the end. And so it navigates to the end of the maze. Or it could be objective non-robust and it learned an incorrect proxy, which was get to the green arrow. And so it navigates to the green arrow. And if you're only looking at the behavior on the training distribution, you can't distinguish between the model which is trying to get to the green arrow and the model which is trying to get to the end of the maze, because the training distribution, those are sort of not identifiable. You can't sort of distinguish between them by looking at behavior. And so if we want to ask the question, how likely is it that we will end up with models which generalize in one way versus models which generalize in another way? We have to look at the other thing than just the behavioral incentives, which is causing models to fall into one category or the other, and that is the inductive biases. The reason that your training process would produce a model which is going to generalize in one way or generalize in another way, despite having the same training performance, is all going to come down to what is incentivized by the inductive biases of that training process. And to understand what's incentivized by the inductive biases of a training process, we have to look at the model's internals. Because the inductive biases aren't just about what's happening here at this point, the inductive biases, right? All of the behavior on the training distribution is the same. So the only difference is what are the inductive biases incentivizing in terms of the internals of the model? Are the inductive biases going to incentivize the sorts of models that have particular properties or models that have other properties? And fundamentally, that's sort of where you have to look if you want to start answering the question of what you're going to get in this sort of standard machine learning setting, because that's the sort of thing which is going to determine what option you end up with when you're in this sort of unidentifiable position.
Yeah, so it sounds like one thing that you notice reading this paper is that it seems very focused on the case of distributional shift, right? Like you're interested in generalization, but not in the like generalization bound sense of like, from the training distribution to the training distributions with samples you haven't literally seen, but some kind of like different world. I'm like, why can't we just train on the distribution that we're going to deploy on? Why is this a problem?
Yeah, so that's a really good question. So I think there's a couple of things going on here. So first, one thing that's worth noting is that I think a lot of times people read the paper and be like, well, like what is going on with this sort of deployment distribution? Sometimes we just do online learning. Sometimes we just do situations where we're just going to keep training. We're just going to keep going. Like, why can't we sort of understand that? And I think basically my argument is that those situations are not so dissimilar as you might think. So let's, for example, consider online learning. I'm going to try to just keep training it on every data point as it comes in and keep sort of pushing in different directions. Well, let's consider the situation where you're doing online learning and the model encounters some new data point. We still want to ask the question, for this new data point, will it generalize properly or will it not? And we can answer the question, will it generalize properly or will it not on this new data point by looking at all of the previous training that we've done was a training environment of sorts. And this new data point is a deployment environment of sorts, where something potentially has changed from the previous data points to this new data point. And we want to ask the question, will it generalize properly to this new data point? Now, fundamentally, that generalization problem is not changed by the fact that after it produces some action on this data point, we'll go back and we'll do some additional training on that. There's still a question of how is it going to generalize to this new data point? And so you could think of online learning setups and situations where we're trying to just keep training on all the data as basically all they're doing is they're adding additional sort of feedback mechanisms. They're making it so that if the model does do something poorly, maybe we have the ability to sort of have the training process intervene and correct that. But fundamentally, that's always the case. Even if you're doing a deployment where you're not doing online learning, if you notice that the model's doing something bad, there are still feedback mechanisms. You can like try to shut it down. You can try to like, look at what's happening and retrain a new model. There's always feedback mechanisms that exist. And if we sort of take a higher level step and we sort of think about what is the real problem that we're trying to solve, the real problem we're trying to solve is situations in which machine learning models take actions that are so bad that they're unrecoverable. That our sort of natural feedback mechanisms that we've established don't have the ability to sort of, account for and correct for the sort of mistake that has been made. And so, an example of a situation like this, Paul talks a lot about this sort of, Paul Cresciano talks a lot about this sort of unrecoverability. One example would be Paul has this post, What Failure Looks Like. And in the What Failure Looks Like post, Paul sort of goes into the situation where you could imagine, for example, a sort of cascade of problems where, one model sort of goes off the rails because it has some proxy and it starts optimizing for the wrong thing. And this causes other models to go off the rails. And you sort of get a cascade of problems that creates unrecoverable situation where, you end up with a society where we put models in charge of all of these different things. And then, as one goes off the rails, it pushes others off distribution. Because as soon as you get one sort of model doing something problematic, that now puts everyone else into a situation where they have to deal with that problematic thing. And that could itself be off distribution from the things we just had to deal with previously, which increases the probability of those other models failing, and you get this sort of cascade. I'm not saying this is the only, I think this is one possible failure mode, but you can see that it's sort of one possible failure mode that is demonstrating the way in which like the real problem is situations in which our feedback mechanisms are insufficient. And you will always have situations where your feedback mechanisms could potentially be insufficient if it, does something truly sort of catastrophic. And so what we're trying to prevent is it doing something so catastrophic in the first place. And to do that, you have to pay attention to the generalization, because every time it looks at a new data point, you're always relying on generalization behavior to sort of do the correct thing on that new data point.
So when you say generalization behavior, you mean like, it's going to encounter a situation, and I guess I'm not sure why like just normal ML isn't enough. Like generalization bounds exist, like why can't we just train on a distribution, deploy, you get different samples from that distribution, so it's a little bit different, but like generalization bounds say that like, it's just not going to be so bad. Why isn't that like the end of the story?
Yeah, so I think that a lot of these generalization bounds rely on a particular assumption, which I think is quite questionable, which is the Iid assumption. The assumption that, in fact, like the deployment distribution and the training distribution, that we can actually create take Iid samples, that there's that we can create particular bounds between the divergence between the distributions or things like this. In practice, all of these sorts of assumptions just I think basically just don't hold. And there's ways in which there's a lot of sort of obvious ways in which they don't hold. There's always things that are sort of changing about our environment. There's always sorts of various different things. I mean, you can imagine just the fact that the date advances, the fact that various things are happening in the world that you might not be able to anticipate. And obviously there are ways to try to address these problems in the sort of standard practice of machine learning. So a very standard thing to do is adversarial training. So you might have a situation where you're like, well, we expect that the distribution is going to vary in a bunch of different ways. We can try to sample some of the ways in which we expect the distribution might vary and train on those things. But there can still be a lot of problems that happen even in that situation. So one of the things that we talk about in the paper that I think is sort of becomes particularly problematic sort of when you start getting into these situations where you've really done a good job at doing adversarial training and tried to train away a lot of the sort of naive, sort of simple ways in which you might end up with, a green arrow optimizer versus a, end of the maze optimizer, is something that we call deceptive alignment. And deceptive alignment is a sort of particularly pernicious case of a sort of MESA optimizer, which has a MESA objective that is sort of different from the ideal loss function. And the particular case of deceptive alignment is a situation in which you have a model, and that model, let's say, has some, proxy objective. It's trying to get to the green arrow or whatever. But it realizes that it's inside of a training process, and that training process is going to select it for getting to the end of the maze rather than getting to the green arrow. And so it realizes that the correct instrumental strategy to be able to get to the green arrow in the future is to currently try to get to the end of the maze so that it will stay around in the training process and won't be modified to go to the green arrow instead. And then eventually at some point, maybe it gets the ability to take some action, maybe you just deploy it. And now when it's in deployment, it can go to the green arrow a bunch of times and you won't correct for it. or it otherwise gets into some situation where the correction mechanisms, the feedback mechanisms that you have are no longer sufficient to prevent it from being able to do like the true proxy objective that it learned. And this is particularly concerning because if you're in a deceptive alignment situation, so the sort of adversarial training setup no longer really works. Because if you think about a deceptive alignment system, it's going to be actively looking for any sort of possible sort of differences between the train distribution and the deployment distribution to let it know that now it's in a situation where it can sort of do what it wants and it doesn't have to be as afraid of sort of corrective feedback. And so there's a lot of examples of the sorts of things that a sort of deceptive model might be looking for. Paul Cristiano has this one example that I think is kind of sort of fun. And it's not necessarily realistic, but it just goes to show the sort of way in which this could happen, which is this sort of RSA 2048 example. So the RSA 2048 example goes like this. You can imagine, so RSA 2048 is this really large pseudoprime. There's this sort of challenge to try to factor RSA 2048.
Sorry, what's a pseudoprime?
It's like a product of two large primes.
Okay.
I think. Yeah. I might be using the terminology wrong. I'm pretty sure, whatever. It's the product of two very large primes. But finding that factorization, finding the like two very large primes that like make up this very large number is very challenging and computationally difficult. And it's sort of beyond the computational abilities of like modern computers, and like are like, I don't know, at least there's a challenge to try to factor it, and nobody has yet been able to do so. But it's the sort of thing that like probably will have enough compute that somebody will eventually get around to like being able to factor it in the future. And so you can imagine a situation where you have a deceptive model, and it's like, well, I don't know when I'm going to be I'm going to be deployed, but at some point probably I'll be in a deployment situation where like I have lots of power and I can like just sort of do whatever I want. And so I'll choose to look for a factorization of RSA 2048. And if I see such a factorization, then I can be pretty sure that I'm no longer in training, because the people training me don't have the compute available to factor RSA 2048. But probably at some point somebody's going to factor it. And so I can be pretty sure that if I see a factorization of RSA 2048, that I'm no longer in training, and I can be pretty sure that eventually I will see such a factorization. And so it's sort of a general, sort of pointing to this sort of general problem of when you try to do adversarial training, you're putting yourself in this sort of situation where you have to be able to, it's sort of this P versus NP thing, where like you're putting yourself in a situation where you have to be able to actually like generate all of the sort of possible counterexamples, whereas the model is in a much easier position. It only has to be able to do the checking. It only has to be able to check whether it is in such a situation. And there's just a lot of things where it's easier to check than it is to generate. The sort of factorization is an example of that. It's a lot easier to check that you have a factorization than it is to generate such a factorization. And this is sort of a general thing, like I was saying, that comes from the fact that there are different complexity classes that vary based on, we can think about NP as being the complexity class of things which are like relatively easily checkable, and P as being the complexity class of things which are relatively easy to actually generate. And these are, I don't know, we think that these are distinct. So there's likely lots of problems like this. Even if we're not thinking about things as sort of rigorous mathematically as RSA 2048, there's just a lot of things about the world that are easier to check than they are to generate. And so that means that if you have a model which is actively looking for differences, your like procedure of let's just try to generate a bunch of differences is no longer likely to work.
Yeah, I think this is... So there's a lot in that answer that I can get back to. One thing that it does remind me of is, often people do talk about adversarial training, and it always strikes me that like it seems like if you want to really make that work, you need much better interpretability tools than we have at the moment, precisely to check this kind of thing. Like, what is the model checking? Like to really find the worst case scenario, you need to know a lot about the model, right? So I guess I'm wondering, do you think that's right, or do you have any thoughts about that?
I think that's exactly right. So I have a post that talks about relaxed adversarial training, which is terminology that comes from Paul Cristiano. And basically the idea there is, well, how can we improve this adversarial training setup? Well, instead of doing adversarial training on the model's inputs, we can try to do it on the model's internals. We can try to sort of generate descriptions of situations in which the model might fail, try to generate sort of like possible sort of like activations for which the model might fail. And these problems might be significantly easier than actually trying to generate an input on which the model fails.
Cool. So there's a lot to get back to. I want to get back to basics a little bit, just about mesa optimizers. So one of the examples you use in the post is like, you can sort of think, at least, for the sake of example, you can think of evolution as like some optimizer, and evolution has produced humans. and humans are themselves optimizers, for such and such thing. And I wanted to get a little bit more detail about that. So I'm a human, and a lot of the time I'm like almost on autopilot, or I don't like. For instance, I'll be sort of acting on some instinct, right? Like a loud noise happens and I kind of jump. Sometimes I'll be doing what I've previously decided to do, or like maybe what somebody's told me to do. So, for instance, like we just arranged this interview, and I know I'm supposed to be asking you questions, and like I'm because we already penciled that into the calendar. That's what I'm doing. Often what I'm doing is like very local means end reasoning. So I'll be like, oh, I would like some food. I'm hungry, so I guess I would like some food now. So I guess I'm going to cook some food, like that kind of thing, which is different from what you might imagine of like, oh, I'm gonna like plan. I'm gonna think, what I'm gonna think of like all the possible like sequences of actions I could take, and I'm gonna search for like which one maximizes like how rich I end up in the future, or some altruistic objective, maybe if you want to think nicely of me or something. So am I a mesa optimizer? And if I am, what's my mesa objective?
Yes, that's a really good question. So, I'm happy to answer this. I will like just warn. I think that my personal opinion is that it's it's like it's easy to go astray. I think thinking too much about the sort of evolution in humans example and what's happening with humans, and like forget that like humans are not machine learning
Hmm.
models, and like there like are real differences there. But I will try to answer the question. So I think that so if you think about it from a sort of computational perspective, it's just not very efficient to try to spend a bunch of compute for every single action that you're going to choose to try to compare it to like all of these different possible opportunities. But that doesn't mean you're not doing search. It doesn't mean you're not doing planning, right? So you can think about, one way to model what you're doing might be, well, maybe you have a bunch of heuristics, but you change those heuristics over time, and the way in which you change those heuristics is by doing sort of careful search and planning or something. Um, I don't know exactly what the correct way is to describe the human brain, and like what algorithm it internally runs and like how it operates. But I think it's a good guess to say, and pretty reasonable to say, that it is clearly doing search. It is clearly doing planning. It is clearly, at least sometimes, and like you were saying, it would be computationally, intractable to try to sort of do some massive search every time, you think about, you're going to move a muscle or whatever. But that doesn't mean that you can't like and on for particular actions, for particular strategies, develop long-term strategies, think about sort of possibilities for like, consider many different strategies, select them according to like whether they satisfy whatever you're trying to achieve. And and that obviously also leads to the second question, which is, well, what is the MACE objective? What is it that you might be trying to achieve? Um, this is obviously very difficult to answer. I mean, people have been trying to answer the question, what are like human values for forever, essentially. Um, I don't I don't think I have the answer, and I don't think that I don't like expect us to get the answer to this sort of thing. But I nevertheless think that like there is a meaningful sense in which you can say that humans clearly have goals, and not just in a behavioral sense, in like a mechanistic sense. I think there's a sense in which you can be like, look, humans select strategies. They like look at different possible things which they could do, and they choose those strategies which like perform well, but which like have good properties according to the sorts of things they're looking for. They try to choose strategies which put them in a good position. They try to do strategies which like make the world a better place. They try to do strategies which like people have lots of things that they use to select the different sorts of strategies that they pursue, the different sorts of heuristics they use, the different sorts of plans and policies that they adapt. And so I think it is meaningful to say and correct to say that humans are MESA optimizers of a form. Are they a central example? I don't know. I think that they're like relatively non-central. I think that like they're not the like example I would want to like have first and foremost of like MESA optimization, but they're a meaningful example because they are a like the only example that we have of like a training process of like evolution being able to produce a like highly intelligent, capable system. So they're useful to think about certainly. Though like we should also expect there to be differences.
Yeah, that makes sense.
But I think they basically fit into the framework.
Yeah, that makes sense. I guess I'm just asking to get a sense of like what a mesa optimizer really is. And I guess your answer is interesting because it sort of suggests that like if I like do my start of year plan or whatever and like do search through some strategies and then like execute, like I'm like even when I'm in execution mode I'm still an optimizer. I'm still a mesa optimizer. Which is interesting because it sort of suggests that if like one of my plans is like, okay, I'm going to play Go, and then I like, open up a game, and then I start doing planning about like what moves are going to win. Am I a mesa optimizer when I'm doing that?
I mean, so my guess would be like not really. You're still probably using exactly the same optimization machinery to do Go as you are to like plan about whether you're going to go do Go. And so in some sense, it's not that you did so like for a Mesa optimizer would have to be a situation in which you internally did an additional search over possible like optimization strategies and possible like models to do optimization and then like selected one.
Okay.
If you're reusing the exact same optimization machinery, you're just one optimizer and you're like you like are optimizing for different things at different points.
Okay. That gives me a bit of a better sense of what you mean by the concept. So I have a few more questions about this. So one thing you do, I believe in the introduction of the paper, is you distinguish between MESA objectives and behavioral objectives. I think the distinction is supposed to be that my MESA objective is the objective that's like, internally represented in my brain. And my behavioral objective is the objective you could recover by asking yourself, okay, looking at my behavior, what am I optimizing for? In what situations would these things be different?
Yeah, so that's a great question. So I think that in most situations where you have a meaningful MESA objective, we would hope that your definitions are such that the behavioral objective would basically be that MESA objective. But there certainly exist models that don't have a meaningful MESA objective. And so the behavioral objective is therefore in some sense a broader term because you can look at a model which isn't internally performing search and you can still potentially ascribe to it some sort of objective that like it looks like it is following.
What's an example of such a model?
I mean, you can imagine something like, maybe you're looking at like, I think, for example, a lot of like current reinforcement learning algorithms potentially might, reinforcement learning models might potentially fall into this sort of category. If you think about, I don't know, it's difficult to speculate on like exactly what the internals of things are, but like my guess would be if we think about something like OpenAI 5, for example, that like it certainly looks.
Can you remind
like these
listeners what OpenAI 5 is?
Sure. OpenAI 5 was a sort of project by OpenAI to solve Dota 2, where they built agents that are able to sort of compete on a like relatively sort of professional level at Dota 2. And I think if you think about some of these agents, these sort of the OpenAI 5 agents, I think that my guess would be that the OpenAI 5 agents don't have like very coherent sort of internally represented objectives. They probably have like a lot of sort of heuristics. Potentially there's some sort of search going on, but my guess would be not very much, such that like you wouldn't really be able to ascribe like a very coherent MESA objective. But nevertheless, we could look at it and be like, there's clearly a sort of coherent behavioral objective in terms of trying to win the Dota game. And we can understand why that behavioral objective exists. It exists because if we think about OpenAI 5 as being a sort of grab bag of heuristics and all of these various different things, those heuristics were selected by the sort of base optimizer, which is the gradient descent process, to sort of achieve that behavioral goal. And one of the things that we're sort of trying to hammer home in risk and learn optimization is that there's like a meaningful distinction between that base objective, the sort of loss function that the training process is optimizing for, and if your model actually itself learns an objective, what that objective will be. And sort of it's easy because of the fact that in many situations the behavioral objective looks so close to the loss function to just sort of conflate the ideas and assume that well, we trained OpenAI 5 to win Dota games. It looks like it's trying to win Dota games, so it must actually be trying to win Dota games. But that last step is potentially fraught with errors, and so that's sort of one of the sort of points that we're trying to make in the paper.
Great. Yeah. Perhaps a more concrete example, would a thermostat be an example of a system that has a behavioral objective, but not necessarily a MESA objective or an internally represented objective?
Yeah, I think the thermostat is a little bit of an edge case because it's like, well, does the thermostat even really have a behavioral objective? I think it kind of does, right? I mean, it's trying to like stabilize temperature at some level, but it's so sort of simple that I don't know. What is your definition of behavioral objective? I don't know. Probably, yeah, thermostat
Cool.
is a good example.
So I wanted to ask another question about this this sort of interplay between this idea of like planning and internally represented objective. So this is a little bit of a troll question. So I'm sorry, but suppose I have my program, right? I have this variable called my_utility, and like I'm writing a program to navigate a maze quickly. That's what I'm doing. In the program, there's a variable called my_utility, and it's assigned to the longest path function. And I also have a variable called my_maximizer, that I'm going to try to maximize utility with. But I'm actually a really bad programmer. So what I assigned to my maximizer was the argmin function. So the function that like it takes another function and like minimizes that function. So that's my maximizer. It's not a great maximizer. And then the act function is my maximizer applied to my utility. So here, the sort of way this program is structured is, if you read the variable names, is there's this like objective, which is to get the longest path. And the way you maximize that objective is really bad. And you use the like minimization function. Yeah, according to you, what is the... So this is a Mesa optimizer because I did some optimization to come up with this program. According to you, what's the Mesa objective of this?
Yeah, so I think that this goes to show something really important, which is that if you're trying to look at a trained model and understand what that model's objective is, you have to like have transparency tools or some means of being able to look inside the model that like gives you a real understanding of what it's doing, so that you can like ascribe a meaningful objective. You can imagine a situation. So I think clearly the answer is, well, the Mesa objective should be the the negative of the thing which you actually specified as because you had some variable name which said maximize, but in fact you're minimizing. And so the real objective, if we were sort of trying to extract an objective which is sort of meaningful to us, would be
and to be just so the listeners don't have to keep that all in their heads. The thing this does is like finds the shortest path, even though my underscore utility is assigned to longest path. But you were saying.
Right. And so I think that what that goes to show, though, is it goes to show that if you had sort of a level of interpretability tools, for example, that enabled you to see the variable names, but not the implementation, you might be significantly led astray in terms of what you expected the Mesa objective to be of this sort of model. And so it goes to show that there's like difficulty in really properly extracting what the sort of model is doing, because the model isn't necessarily built to be easy to extract that information. It might have sort of weird, red herrings or things that are like implemented in a strange way that we might not expect. And so if you're in the business of trying to figure out what a model's Mesa objective is by looking at it, you have to run into these sorts of problems where, things might not be implemented in the way you expect. You might sort of have something which you expect to be a maximizer, but it's a minimizer or something. And so you have to be able to deal with these sorts of problems if you're trying to look at models and figure out what they're.
So I guess my the question that I really want to get at here is this is obviously a toy example, but like typically optimizers, like at least optimizers that I write, they're not necessarily perfect, right? They don't find the thing that like that I'm trying to maximize some function when I'm writing it, but the thing doesn't actually like maximize the function. So I guess like part of what I'm getting at is like to what extent, if there's going to be any difference between like your Mesa objective and your behavioral objective, like to what extent it seems like either you've got to pick the variable name that has the word utility in it, or you've got to say like, well, the thing that actually got optimized was the objective, or like you might hope that there's a third way, but I don't know what it is. So do you think there's a third way? And if so, what is it?
Yeah, so I guess the way in which I would describe this is that fundamentally we're just trying to get good mechanistic descriptions. And when we say Mesa optimizer, I mean Mesa optimizer to refer to the sort of model which has something we would look at as a relatively coherent objective and like optimization process. Obviously, not all models have this, right? So there's lots of models which like don't really look like they have a coherent optimization process and objective. But we could still try to get a nice mechanistic description of what that sort of model would be doing. When we talk about Mesa optimizers, we're referring to models which have that sort of nice mechanistic description, which look like they have an objective and they have a search process which is trying to sort of select for that objective. I think that the sort of the way in which we sort of are getting around these sorts of unidentifiability problems, I guess, would be, well, like we don't claim that this works for all models. Lots of models just don't fall into the category of Mesa optimizers. And then also we're like not trying to like come to a conclusion about what a model's objective might be only by looking at its behavior. We're just asking if the model is structured such that it has a like relatively coherent optimization process and objective, then what is that objective? And it's worth noting that this obviously sort of doesn't cover the full scope of possible models, and it doesn't necessarily cover the full scope of possible models that we are concerned about. But I do think it covers a like large variety of models, and we make a lot of arguments in the paper for why you should expect this sort of optimization to occur, because it sort of generalizes well, it performs well on a lot of simplicity measures, it has this sort of ability to sort of compress really complex policies into relatively simple search procedures. And so there's reasons that you might expect that we go into in the paper this sort of model to be the sort of thing that you might find. But it's certainly not the case that it's always going to be the sort of thing you find.
Okay, that makes sense. So I guess the final question I want to ask to get a sense of like what's going on with mesa optimization. How often are neural networks that we train mesa optimizers?
Yes, that's a really good question. I have no idea. I mean, I think this is the sort of thing that is like an open research problem. My guess would be that most of the systems that we train currently don't have this sort of internal structure. Um, there might be some systems which do. We talk a little bit in the risk and optimization paper about some of the sorts of related work that might sort of have these sorts of properties. So one of the examples that we talk about is the sort of RL squared paper from OpenAI, where in that paper they sort of demonstrate that you can create a sort of reinforcement learning system which sort of learns how to do reinforcement learning by sort of passing it through many different reinforcement learning environments and asking it to sort of along the way figure out what's going on each time rather than explicitly training on like that specific reinforcement learning environment. This sort of thing seems like closest to the sort of thing that we're pointing at in terms of like existing research. But of course, the problem is that our definition is one which is mechanistic and requires the understanding of is it actually doing search, which is not really something we know because we don't have the ability to really look inside of our models and know whether they're doing search or not. So is it happening with current models? I don't know. I think that like we certainly see like some of the sorts of failures in terms of like, sometimes we see models which try to pursue proxies to the objectives which they're trained under. But those proxies aren't necessarily the sorts of ones which are like very objective, robust. They might not be sort of a really good coherent search process, which generalizes well and is able to sort of pursue that proxy intelligently and coherently, even off distribution, which fundamentally is what we care about. Because if you think about the sort of 2D robustness picture, if you have a situation where a model is very sort of capability robust, is really good at doing optimization, it's able to sort of take really sort of coherent, capable actions, but it's doing so for a sort of non-robust objective, an objective that is not the one which we actually wanted to achieve, you end up in a sort of bad situation because you have a very capable model which is doing the wrong thing. We certainly see some amount of objective non-robustness, but in some sense we sort of also see that along with capability non-robustness. Like a lot of cases when you sort of look at models off distribution, they just sort of are bad. They don't do like really coherent things. And so we're in a situation where like these sorts of notions haven't yet come apart completely because we haven't yet sort of gotten good enough at capability robustness, having good enough at producing models which are capable of doing really coherent optimization on and off distribution to be able to get to a situation where they have like potentially an objective which might be meaningful.
Okay, cool. So I now want to move on a little bit to how we might produce mesa optimizers. So one reason you give for why or when mesa optimization might happen is when there's a lot of computation available at inference time or runtime relative to how much computation is devoted to training the system. And I guess this is because like the optimization has to happen at some point, and if it can happen at like inference time, like when the model's running, then you don't do it so much when you're training. So I guess I'm wondering, do you expect this situation of like a lot of computation being used at inference time relative to during training? And if so, why? And also, how big a deal is this, do you think?
Yeah, so I guess I'm not sure I 100% agree with that description. So I think
Okay.
that the thing which I would just say is that the more compute your model has available to it at inference time, the more likely it is to be a Mesa optimizer. I think the additional question of how the compute available at inference time versus the compute available at training time, like compare to each other, the sort of relative differential, I think is more complicated. So, for example, I think that in fact, the more compute you have available at training time, the sort of better you are at selecting for models which are sort of perform very well according to your inductive biases. So, so this is a little bit complicated. So, one story for sort of why I believe this. So, you think about something like double descent. So double descent is a phenomenon which has sort of been sort of demonstrated to exist in sort of machine learning systems, where what happens is you start training your machine learning model, and initially you sort of get this sort of standard learning theory curve where the sort of training error goes down and the sort of test error goes down and then goes back up as you start overfitting. And then the sort of insight of double descent is, well, if you keep training past zero training error, your your test error actually starts to go back down again and can potentially get lower than it ever was earlier. And the reason for this is that if you keep training, if you put enough compute into just training past the point of convergence, you end up into a situation where, well, you're selecting for the model which performs best according to the inductive biases of your sort of machine learning system, which fits the data. Whereas if you only train to the point where it gets zero training error, then stop immediately, there's a sense in which there's sort of, well, there's only sort of potentially maybe one model. It's just the sort of first model that it was able to find, which fit the training error, fit the training data. Whereas if you keep training, it's selecting from many different possible models, which might fit the training data, and finding the sort of simplest one. And one of the arguments that we make for why you might expect MESA optimization is that MESA optimizers are relatively simple models. Search is a pretty sort of simple procedure, which is not that complicated to sort of implement, but has the ability to sort of, in fact, do tons of different sort of complex behavior at inference time. And so it's sort of search, you can be thought of as a form of compression. It's a way of taking these sort of really complex policies that depend on lots of different things happening sort of in the environment and compressing them into this sort of very simple search policy. And so if you're in a situation where you're putting a ton of compute into training your model, then you might expect that sort of according to something like this double descent story, that what's happening is the more compute you put, the sort of more your training process is able to select the sort of simplest model which fits the data, as opposed to just the sort of first model that it finds that fits the data. And the simplest model that fits the data, we argue is more likely to be a MESA optimizer. And so in that sense, I would actually argue that sort of the more training compute you do, the more likely you are to get MESA optimizers, and the more inference time compute you have, the more likely to get MESA optimizers. And the reason for the inference time compute is the sort of similar to the reason you were saying, which is that inference time compute enables you to do more search. It makes search more powerful. Search does require compute. You have to sort of do this. It takes a certain amount of compute to be able to do the search, but it has the benefit of this sort of compression of, you have to do a bunch of compute for sort of performing the search, but as a result, you get the ability to have a much more sort of complex policy that's able to be sort of really adapted to all these different situations. And so in that sense, the sort of more compute on both ends, I would expect to lead to sort of more likelihood of MESA optimization. It is worth noting there's sort of some caveats here. So in practice, we generally don't train sort of that far past convergence. I think that there's also still a lot of evidence that especially if you're doing things where, for example, you do very early stopping, where you only do a very small number of gradient descent steps after sort of initialization, there's a sense in which that also is very sort of strong on inductive biases, because you're so close to initialization, the inductive biases of, well, the things which are relatively easy, sort of simple to initialize, which take up a large volume in the sort of initialization space, those are the sorts of things which are be very likely to find. And so you still end up with sort of very strong inductive biases, but actually it's sort of different inductive biases. There's not a lot of great research here, but I think it's still the case that when you're doing a lot of sort of training compute on very large models, if you're doing sort of really early stopping or training much past convergence, you're ending up in situations where the sort of inductive biases matter a lot, and you're selecting for sort of relatively simple models, which I think sort of leads to selecting for search and selecting for optimization and selecting for MESA optimizers.
Okay, so that makes sense. So yeah, this gets me to another question. One of the arguments that you make in the paper is this idea that MESA optimizers are just more simple. They're more compressible. They're easier to describe, and therefore they're going to be favored by inductive biases or by things that prefer simplicity. But this presumably depends on the language that you're using to describe things. So I'm wondering, in what languages do you think it's the case that optimizers are simple? And in particular, I'm interested in the sort of quote unquote languages of the L2 norm of your neural network, and the quote unquote language again of the size of say a multi-layer perceptron or a CNN. How many layers it has.
Yes, this is a really good question. So I mean, the answer is I don't know. So I don't know the extent to which these things are in fact easy to specify in sort of concrete machine learning settings. How hard is it to actually if you were to sort of try to write an optimization procedure in sort of neural network weights, how difficult that would be to do, and sort of how much sort of space do those sorts of models take up in the sort of neural network prior? I don't know. My guess is that it's not that hard, and it certainly depends on the architecture. But we can start if we start just very simple architecture. We think about sort of very simple sort of multi-layer perceptron or whatever. Can you encode optimization? I think you can. So you can do sorts of things where you can I think depth is sort of like pretty important here because it gives you the ability to sort of work on results over time, create like, many different possibilities, and then like refine those possibilities as you're sort of going through. But I do think it's possible to implement sort of like bare bones sort of search style things in sort of just thinking about a multi-layer perceptron sort of setup. It certainly gets easier when you sort of look at sort of more complicated setups. If you think about something like an LSTM, like a recurrent neural network, you have the ability now to sort of work on like a plan sort of over time in a sort of similar way to, like a human might, like you were describing earlier, where you can like make plans and then sort of execute them. And especially if you think about something like AlphaZero, or even more especially something like MuZero, which explicitly has like a sort of world model that it tries to search over and do MCTS sort of Monte Carlo tree search over that to like find some objective. And the objective that it's searching over in that sort of situation is a sort of value network that is learned. And so you're learning some objective, and then you're explicitly doing search over that objective. Now, we talk about this sort of situation of like hard-coded search in the paper a lot. Things get a little bit tricky because you might also have sort of maze optimization going on inside of any of the individual models. And the situations under which you might end up with that are sort of, well, you might end up in a situation where the sort of search you've given it to be hard-coded is not the sort of search which like it really needs to do to solve the problem. So it's a little bit complicated, but certainly I think that like current architectures are capable of implementing search and being able to do search. There's then the additional question of how simple it is. I think that, so, unfortunately, we don't have really great measures of sort of simplicity for neural networks. We have sort of, very simple measures like Kolmogorov complexity. And there is some evidence to indicate that like Kolmogorov complexity is like at least related to the sort of inductive biases of neural networks. So there's some recent research from one of the co-authors on some of the research was UR Skulls, who's one of the co-authors on risk learner optimization, trying to sort of analyze the sort of what exactly is the prior of neural networks at initialization. And there's some theoretical results there that indicate that like Kolmogorov complexity actually can serve as like a real sort of bound there. But of course, Kolmogorov complexity is uncomputable. For people who are not aware, Kolmogorov complexity is a measure of a description length that is based on finding the sort of simplest Turing machine, which is capable of sort of reproducing that. And so we can look at these sorts of theoretical measures like Kolmogorov complexity and be like, well, it seems like search has a relatively low Kolmogorov complexity. But of course, the actual inductive biases in machine learning and in gradient descent are more complicated, and we don't fully understand them. There is other research. So there's also some research that looks at trying to understand the sort of inductive biases of gradient descent, trying to, it seems like gradient descent generally favors sort of these very large basins. And there's sort of, evidence that these sorts of very large basins seem to match onto sort of relatively simple functions. There's also sort of stuff like the lottery tickets hypothesis, which hypothesizes that the sort of what's happening. So if you train a very, very large neural network, it's going to have a bunch of different subnetworks. Some of those subnetworks at initialization will happen to sort of encode the sort of already be relatively close to the sort of goal that you're going to get to. And then the gradient descent process will sort of be amplifying some subnetworks and sort of de-amplifying other subnetworks. And if you sort of buy into a hypothesis like this, then you're sort of in a situation where, well, there's a question of how likely are sort of subnetworks implementing something like optimization likely to be at initialization. Obviously, the larger your network is, the more sort of possible subnetworks at initialization there are that exist in a sort of combinatorial explosion sort of way, such that as you get to much sort of larger and larger networks, the sort of combinatorial explosion of subnetworks sort of seems like it would eventually cover even things sort of potentially quite complicated. But unfortunately, there's just not that much I can say because our understanding of the inductive biases of neural networks just isn't great. We have like some things which we can talk about simplicity measures and stuff. But unfortunately, at the end of the day, I can be like, well, it certainly seems like search would be relatively simple and likely to learn. But like, I don't have like really strong results for that because we just don't have a great understanding of exactly how these inductive biases operate.
It does sound like one thing you think though is that like you mentioned if you want to do search in something like a multi-layer perceptron, you mentioned that it helps to just have a bunch of layers to refine options and such. So it kind of sounds like you think that if we were selecting on network depth, that would be a kind of simplicity that would disfavor search rather than favoring it. Does that sound right to you?
That does sound right. So the way in which I would describe that is in some ways sort of looking at inference time compute. It's sort of thinking about sort of more like a speed prior. So if you think about a speed prior, something sort of like Yeah. So speed prior is sort of trying to select on models which have a sort of like small time from sort of initialization to sort of completion. So like the actual amount of time it takes to run the sort of function. If you think about sort of depth versus width, if you have a very wide neural network but it's not very deep, then it's actually very fast to run because you just sort of run through that initial step. It might still be computationally expensive, but because you can parallelize the sort of width wise, the actual sort of individual step is relatively fast in a way in which it would sort of be favored by a speed prior. And so one of the things that we do claim in the paper is that these sorts of speed prior like incentives disincentivize Mesa optimization, because Mesa optimization does require the extent the sort of it requires you to be able to have these sorts of multi-level like long sort of relatively long sort of inference time sort of computations. And if you sort of restrict your model to not be able to do these sorts of relatively long inference time computations, then it's probably going to be less likely to be able to do search, to be able to do Mesa optimization. So certainly in that sense, I think that there is a sort of distinction there between like sort of a simplicity prior and a sort of minimal circuit speed prior thing, where with the speed prior you get sort of different incentives, and there's a sort of distinction where if you sort of are selecting on depth, you're sort of doing something more like a sort of speed prior, which sort of changes things.
What do you think the important difference here is between time and space? Because it sounds like you're saying, well, if you have a lot of time to compute, then you can be an optimizer. But if you just have a lot of space, then you can't be an optimizer. Like,
Yeah.
why is there this asymmetry? Doesn't special relativity tell us that these things are the same?
Well, okay. So here's a really simple sort of analogy to sort of think about this: is let's say I have a lookup table as my model versus like a optimizer. The lookup table that is like equivalent to the optimizer behaviorally is going to be really large because it has to explicitly encode all of these different things that it's going to do. But it's also going to be really fast because you just look at the lookup table, you like figure out what it's going to do, and then you do that action.
Doesn't it? Hang on. Why is it fast? Doesn't it take exponentially long to figure out like where? Like you go through the lookup table and there's like a billion entries, so you have to like go really
hash
far.
map one lookup something something something.
I mean, not worst case, right? Like eventually you get collisions.
Amortized expected O of one.
All right.
I think this is actually like in fact the case. If you look at like there is analysis of like looking at sort of minimal circuits and like speed priors and stuff, trying to understand like what would happen in these sorts of situations. And in fact, I think lookup tables like are really good because they're in fact quite fast. Like if you have all of the information already encoded, yes, you need to like have be able to generate some key, be able to look it up. But I don't know, there are like mechanisms that they're able to do that relatively quickly. A hash map being one of them. Even just looking it up in like a binary search tree or something is still not going to be that bad potentially. And so if you have a lookup table, it can be relatively fast, but it takes a lot of space. Whereas if you have an optimization system, it has to be relatively slow because it has to actually like come up with the like possibility of like all of the different possible like options and like then select one of them. And that process is going to take it takes compute, it takes time. It has to actually like look through different options and select them. And you can have heuristics to try to narrow down the field of possible things which you're going to look for, but you still need to look. You're still probably going to need to look at a bunch of different things to be able to select the sort of the correct one. And so we can think about in this situation, the optimizer has a really sort of large, it has a larger sort of inference time compute, but it has a smaller description because you don't have to explicitly write down in the description of this optimizer all of the different actions that's going to take for all of these different things. It just needs to have a sort of general procedure of, well, let's look at an objective, let's do some search to try to select for something. Whereas if you think about the lookup table, it has to explicitly write all of these things down, then in inference time, it sort of gets benefits. And this sort of thing, this sort of trade-off between, space and time, occurs a lot in sort of, computational complexity setups. A lot of times you think about the sort of, you'll take a function and then you'll sort of memoize it, which is a sort of procedure of, well, I have this function, I call it a bunch with different arguments. I can make it faster if I'm willing to spend a bunch of space storing all of the different possible results that I generally call it with. And as a result, you get a faster function, but you have to spend a bunch of time, a bunch of space, sort of storing all these different things. And so you sort of might expect a sort of similar thing to happen with with neural networks, where if you're able to spend a bunch of space, you can store all of these different things, and it sort of doesn't have to spend all of this time computing the function. Whereas if you sort of force it to sort of compute the function every time, then it sort of then it isn't able to store all these different things. It has to sort of recompute them.
Okay, so Yeah, I mean, one thing this makes me think of is like, the paper is sort of talking about this, these risks from like these learned optimizers, and optimizers are these things that are like doing search, like they're actually doing search like at inference time. And they're not these things that, are behaviorally equivalent to things that do search at inference time. And I guess we already got to a bit about like why you might be worried about these mesa optimizers, and we're going to avoid getting them. And I'm wondering, like, is mesa optimizer the right category? If it's the case that like, oh, we could instead search for things that are like our base optimizer, we could instead try to like get these systems that have like they're really quick at inference, and then they're definitely not going to be mesa optimizers because they can't optimize. But of course, they definitely could be these tabular forms of mesa optimizers, which is presumably just as big a problem. So like, I guess this is making me wonder: is mesa optimizer like the right category?
Yes, that's a good question. So I think that if you think about the sort of tabular Mesa optimizer, how likely would you be to actually find the sort of tabular Mesa optimizer? I think the answer is very unlikely, because the sort of tabular Mesa optimizer sort of has to encode all of this sort of really complex like results of optimization explicitly in a way which I think sort of, especially when you get to really complex, really diverse environments, just takes up sort of so much sort of space and explicit memorization. But not just memorization. Like you have to be able to memorize like what your deployment what your sort of like out of distribution behavior would be according to like performing some complex optimization, and then like sort of have some way of explicitly encoding that. And that's sort of like I don't know, I think quite difficult.
But how could we get presumably like if we're doing this selection on short computation time, well, we do want something that actually succeeds at this really difficult task. So how is that any easier than like it seems like if you think there are a bunch of these like potential mesa optimizers out there, and they're behaviorally equivalent, surely the like lookup table for like really good behavior is behaviorally equivalent to the lookup table for the things that are these like dangerous mesa optimizers.
Sure. So the key is inductive biases and generalization. So if you think about it, like there's a reason that we don't train lookup tables and we instead train neural networks. And the reason is that if we just train lookup tables, if you're doing tabular Q learning, for example, tabular Q learning does not have as good inductive biases. It is not able to learn like the nice sort of simple and expressive functions that we're trying to learn to like actually sort of understand what's happening. And it's also really hard to train. If you sort of think about tabular Q learning in a sort of really complex setting with like very sort of diverse environments, you're just never going to be able to even get enough data to sort of understand what the results are going to be for all of these different sort of possible sort of tabular setups. And so there's a reason that we don't do tabular Q learning. There's a reason that we use deep learning instead. And the reason is because deep learning has these nice inductive biases. It has the ability to sort of train on some sort of particular set of data and have good generalization performance because you selected a simple function that fit that data. Not just any function that fit that data, but a simple function that fit that data, such that it has a good performance when you sort of try it on other situations. Whereas if you are just sort of doing training on sort of other situations, like a tabular setup or something, you don't have that sort of nice generalization property because you aren't sort of learning these simple functions that fit the data. You're just learning some function which fits the data, and that's the sort of that's sort of the direction I expect machine learning to continue to go, is to sort of develop these sorts of nice inductive biases setups, these sort of situations in which we have like these model spaces where we can sort of have inductive biases that select for simple models in sort of large expressive model spaces. And if you sort of expect something like that, then you sort of should expect a situation where we're not sort of training these sort of tabular models. We're training these sort of simple functions, but the simple functions that nevertheless like generalize well because they're simple functions that fit the data. And it's also worth noting, right, like why simplicity? Well, I think that like, I don't know, there's a lot of sort of research that sort of understands like, it looks like, if you actually look at neural network inductive biases, it does seem like sort of simplicity is like the right measure. Like a lot of these sorts of like the functions which are very likely to exist in initialization, as well as the sorts of like functions that SGD is likely to find, have the sort of simplicity properties in a sort of like, in a way which is actually very closely tied to like, computational description length, like homograph complexity. There's like the sort of the research I was mentioning recently from UR and others was talking about like the Levin bound, which is this sort of particular mathematical result which directly ties us to homograph complexity. And so there's arguments that like what's and there's also sort of a further argument which is just, well, if you think about why do things generalize at all? Why would a function generalize in the world? The sort of answer is something like Occam's razor. It's that, well, the reason that things generalize in the world that we live in is because we live in a world where the actual sort of true descriptions of reality are relatively simple. And so if you look for the sort of simplest description of that sort of fits the data, you're more likely to get something that generalizes well, because Occam's razor is sort of telling you that that's the thing which is actually more likely to be true. And so there's sort of these really fundamental arguments for why we should expect sort of simplicity to be the sorts of measure which is sort of likely to be used. And that we're sort of likely to continue be training these sort of expressive model spaces and then selecting on simplicity rather than sort of doing something like, I don't know, tabular learning.
Okay, so I'm just going to try to summarize you, check that I understand. So it sounds like what you're saying is, look, sure, we could think about like training these, selecting models to be like really fast at inference time, and in that world, all sorts of like maybe you get like tabularized mesa optimizers or something. But like, look, the actual world we're going to be in is we're going to like select on sort of description length simplicity, and we're not going to select very hard on computation runtime. So in that world, we're just going to get mesa optimizers, and you just want to be thinking about that world. Is that right?
I mean, I think that's basically right. I think I basically agree with that.
Okay, cool. All right, so I think I understand you now. So I'm going to switch topics a little bit. So what types, in terms of like, are we going to get these mesa optimizers? Do you have a sense of like what types of learning tasks done in AI do you think are more or less prone to producing mesa optimizers? So like if we just avoided RL, would that be fine? If we like only did image classification, would that be fine?
Yeah, that's a great question. So we do talk about this a little bit in the paper. I think that the RL question is a little bit tricky. So we definitely mostly focus on RL. I do think that you can get mesa optimization in sort of more supervised learning settings. It's definitely a little bit sort of trickier to understand. And so I think it's a lot easier to sort of comprehend a mesa optimizer in an RL setting. I think it is more likely to get mesa optimizers in RL settings. Let's see, maybe I'll start with the other question, though, which is just about the environment. I think that that's sort of a simpler question to understand. I think that basically, if you have really complex, really general environments that require sort of general sort of problem-solving capabilities, then you'll sort of be incentivizing mesa optimization. Because fundamentally, if you think about mesa optimization as a way of sort of compressing really complex policies, if you're in a situation where you have to have a really complex policy that like carefully depends on the particular environment that you end up in, where like you have to look at your environment and like figure out what you have to do in this specific situation to be able to solve the problem, and like reason about like what sorts of things are likely to succeed in this environment versus that environment, you're like requiring these really complex policies that have simple descriptions if they're compressed into search. And so you're sort of directly incentivizing sort of search in those situations. So I think the question is relatively easy to answer in the environment case. In the case of like reinforcement learning versus supervised learning, it's a little bit more complicated. So certainly in reinforcement learning, you have this sort of setup where, well, we're sort of directly incentivizing the model to sort of act in this environment and sort of over sort of, multiple steps generally. And we're sort of acting in the environment over multiple steps. You're sort of, there's a sort of natural way in which sort of optimization can be nice in that situation where, it has the ability potentially also to like, develop a plan and execute that plan, especially if it has, some means of, storing information over time. But I do think that the same sort of thing can happen in supervised learning. So even if you just think about a very simple supervised learning setup, let's imagine like a language model. The language model has to, it looks at some prompt and it has to predict what the sort of future, what the text after that would be by, a human that wrote it or whatever. You could imagine a situation in which a language model like this could be, just doing a bunch of heuristics, has a bunch of understanding of like, the various different ways in which, people write and the various different sorts of concepts that people might sort of have that would follow this, some rules for like grammar and stuff. But I think the optimization is really helpful here. So if you think about a situation where like, well, you really want to look over many different possibilities. Like you're going to have like lots of different situations where like, well, maybe, this is the possible thing which will come next. It's not always the case. There are very few hard and fast rules in language. You'll look at a situation where like, there's like sometimes after like this sorts of thing, there'll be that sort of thing. But like, it might be that you're actually, they're using some other synonym or you're using some other sort of analysis of it. And sort of the ability to sort of, well, maybe we'll just like, come up with a bunch of different sort of possibilities that sort of might be, exist for the next completion, and then evaluate those possibilities, I think is still a sort of strategy which is very helpful in this domain. And it still has the same property of compression. It still has the same property of simplicity. You're in a situation where there's a really complex policy to be able to describe exactly what the sort of human completion of these things would be. And a like simple way to sort of be able to describe that policy is a policy which is, well, searching for the sort of, the sort of correct completion. If you think about what humans are actually doing when they're producing language, they are in fact doing, search for parts of it. You're searching for like the correct sort of way to the best possible word to fill into the situation. And so, if you imagine a model which is trying to do something similar to the actual sort of human process of completing language, then you're sort of getting a model which is sort of potentially doing some sort of search. And so I really do think that even in these sorts of supervised learning settings, you can absolutely get misoptimization. I think it's trickier to think about, certainly, and I think it's probably less likely. But I certainly don't think it's impossible or even unlikely.
Okay. So, yeah, as I guess you kind of mentioned, like, or at least alluded to, suppose I wanted to avoid Mesa optimizers from just being, I just don't want them, So one thing I could do is I could avoid doing things that require modeling humans. So, for instance, like natural language processing or natural language prediction, where you're trying to predict what, like, maybe me, Daniel Filan, would say after some, prompt. And also avoid doing things that require modeling other optimizers. So, like, really advanced programming or advanced like program synthesis or analysis would be a case of this, where, like, some programs are optimizers and you don't want your system modeling optimizers, so you want to avoid that. So a question I have is how much do you think, like, you could do if you wanted to avoid mesa optimizers and you were under these constraints of don't do anything which involves which like for which it would be useful to model other optimizers?
Yeah, so this is a question that I've there's some writing about that I've done in the past. So I think there are some concrete proposals of like how to do AI alignment that sort of I think fall into this sort of general category of trying not to do sort of not produce Mesa optimizers. So I have this post, an overview of 11 proposals for building safe advanced AI, which goes through a bunch of different sort of possible ways in which you might sort of structure a sort of advanced AI system in a way to be safe. Some of those proposals, so one of them is sort of STEM AI, where the basic idea is, well, maybe you sort of try to totally confine your AI to sort of just thinking about sort of mathematical problems, scientific problems. Maybe you want to build like, if you think about something like AlphaFold, you want to just do really good protein folding. You want to do really good like, physics. You want to do really good chemistry. You want to do sort of like, and you can accomplish a lot just by sort of having sort of very sort of domain restricted models that are sort of just focusing on domains like chemistry or protein folding or whatever, that are totally devoid of of humans. There aren't sort of optimizers in this domain. There aren't humans in this domain to sort of model. You're just thinking about these sort of very sort of narrow domains. There's still a lot of progress to be made. And there's a lot of things that you can do just with models along those lines. And so maybe if you just use models like that, there's sort of, you might be able to do sort of, powerful sort of advanced technological feats like, things like nanotechnology or whole brain emulation if you really sort of push it potentially. So that's sort of one route. Another route that I sort of talk about in the 11 proposals post is this idea of microscope AI. Microscope AI is an idea which is due to Chris Olah. Chris sort of has this idea of, well, maybe another thing which we could do is just train a sort of predictive model, a bunch of data. Oftentimes that data, in I think in many of the ways in which sort of Chris sort of produces this, that data might involve humans. So you might still have some human sort of modeling. But the idea would be, well, maybe sort of in a similar way to sort of a language model being less likely to produce Mesa optimization than like a reinforcement learning agent, we could just train a sort of supervised setting, a sort of purely predictive model to try to sort of understand a bunch of things. And then rather than trying to use this model to like directly influence the world as like an agent, we just sort of look inside it with transparency tools, extract this sort of information or knowledge that it has learned, and then use that knowledge to sort of guide human decision making in some way. And so this is another approach which tries not to produce an agent, which tries not to produce sort of an optimizer which acts in the world, but rather just sort of produce a system which learns some things, and then we use that knowledge to sort of do other things. And so there are approaches like this that try to not build Mesa optimizers. I think that these are sort of both the sort of STEM AI style approach and the microscope AI style approach, I think are like sort of relatively reasonable sort of things to be looking into and to be sort of working on. Whether these sorts of things will actually work, it's hard to know, and there's lots of problems. With microscope AI, there are problems like, maybe you actually do produce a Mesa optimizer, like the language modeling example. There's other problems as well. Even with STEM AI, also there's problems where, what can you actually do with this if you're just doing, like all of these sort of very sort of, these physics problems or chemistry problems. If the main use case for your AI is being a sort of, AI CEO or helping you do more AI research or something, it's going to be hard to get a model which is able to do some of those sorts of things without sort of modeling humans, for example. And so there's certainly limits, but I do think that these are like valuable proposals that are sort of worth looking into more.
Okay. Yeah, it also seems like following these like if you really wanted to avoid modeling humans, like these would be pretty significant breaks from the standard practice of AI as like most people understand it, right? Or at least the standard story of like we're gonna develop more and more powerful AIs and then they're just gonna be able to do everything. Like it seems like you're gonna really have to try. Is that fair to say?
Yeah, I mean, I think that there's like a question of exactly how you expect the field of AI to develop. So
Hmm.
you could imagine a situation, and I talk about this a little bit also in like the post. I have a post Chris Ola's views on AGI safety, which sort of goes into some of the sort of ways in which Chris views the sort of strategic landscape. One of the things that Chris thinks about is microscope AI, and one of the sort of ways in which he talks about a way in which you might actually end up with microscope AI being a sort of real possibility would be if you had a sort of major realignment of the machine learning community towards understanding models and trying to sort of look inside models and figure out what they were doing, as opposed to just sort of like trying to beat benchmarks and beat the state of the art with like sort of relatively black box systems. You can sort of think of this as a realignment towards a more scientific view as opposed to a more engineering view. Where sort of currently a lot of the way in which people, I think a lot of researchers sort of approach machine learning is as a sort of engineering problem. It's, well, we want to achieve this goal of like getting across this benchmark or whatever, and so we're going to try to sort of throw our tools at it to achieve that. But you can imagine a more sort of scientific mindset, which is, well, the goal is not to achieve some particular benchmark to build some particular system, but rather to understand these systems and what they're doing and how they work. And from a more sort of, if you imagine a sort of more scientifically focused machine learning community as opposed to a more sort of engineering focused machine learning community, I think you could imagine a sort of realignment that could sort of make microscope AI seem relatively sort of standard and normal.
Okay. So I guess I have one more question about how we might imagine mesa optimizers being produced. Like in the paper, you're doing some reasoning about like what types of mesa optimizers we might see, and it seems like one of the ways you're thinking about it is like there's going to be some parameters that are dedicated to the goals or the mesa objective, and other parameters dedicated to other things. And if you have something like first order gradient descent, it's going to like change the parameters in like the goal thing, assuming all of the parameters in the belief or the planning or whatever parts are staying constant. And one thing I'm wondering is if I think about these like classically understood parts of an optimizer, so or something doing search, right? So like maybe it has perception, beliefs, goals, and planning. Like, do you think there's necessarily going to be different parameters of your machine learned system for these different parts? Or do you think that potentially there might be parts like spread across or parameters divided to different parts, in which case you couldn't reason about quite as nicely about how gradient descent is going to interact with it?
So this is the sort of stuff that gets to the most speculative. So I think anything that I say here has to come with a caveat, which is like we just have no idea what we're talking about when we try to talk about these sorts of things because we simply don't have a good enough understanding of exactly the sorts of ways in which neural networks decompose into pieces. There are sort of ways in which people are trying to get an understanding of that. So you can think about like Chris Ola's sort of circuits approach and sort of Clarity teams trying to understand and sort of decompose into circuits. Also, I know, Daniel, you have your sort of modularity research where you're trying to understand the extent to which sort of you can break neural networks down to sort of coherent sort of modules. I think that all of this stuff is great and sort of gives us some insight into the extent to which these sorts of things are true. Now, that being said, I think that like the actual extent of our understanding here is still pretty minimal. And so anything I say, I think, is basically just speculation. But I can try to speculate nevertheless. So I think that my guess is that you will have sort of relatively coherent like things like to be able to do search, and I think you will get search. You have to do things like come up with options and then select them, and so you have to have at least some point where you're like coming up. You have to have like heuristics to guide like your ability to come up with options. You have to have like in somewhere generate those options and store those options, and then somehow prune them and select them down. And so those sorts of things have to exist somewhere. Now, certainly we found, if you think about, many of the sorts of analysis of neural networks that have been done, there exists the sort of polysemanticity where you can have sort of neurons, for example, that sort of encode for many different possible concepts. And you can certainly have these sorts of things overlapping because the structure of a neural network is such that, it's not necessarily the case that things have to be, totally isolated. One neuron does one particular thing or something. And so it's certainly the case that you might not have these like really nice, you can point to the network and be like, that's where it does the search, that's where its objective is encoded. But hopefully at least we can have like, okay, we know how the objective is encoded. It's encoded via like this sort of combination of neurons there that do this like particular selection that encode like this thing here. I think that I'm optimistic. I don't know. I expect those sorts of things to at least be possible. I'm hopeful that we will be able to get to a point as a sort of field in our understanding of neural networks, our understanding of how they work internally, that we'll actually be able to sort of concretely point at those things and extract them out. I think this would be really good at our sort of ability to be able to address inner alignment and base optimization. But I do expect those sorts of things to exist and to be extractable, even if they require sort of understanding of polysemanticity and the way in which sort of concepts are spread across sort of the network in various different ways.
So I'd like to change topics again a little bit and talk about inner alignment. So in the paper, you, correct me if I'm wrong, but I believe you describe inner alignment as basically the task of making sure that the base objective is the same as the MESA objective. And you give a taxonomy of ways that inner alignment can fail. So there's proxy alignment, where the thing that or specifically that inner alignment can fail, but like you don't know that it's failed. Because, if inner alignment fails and like the system just does something totally different, that's like, normal machine learning will hopefully take care of that. But there are three things you mentioned. Firstly, proxy alignment, where there's some other thing which is causally related to what the base optimizer wants, and your system optimizes for that other thing. There's approximate alignment, which is where you have some objective, your base optimizer has some objective function, and your system learns an approximation of that objective function, but it's not like totally accurate. And thirdly, sub-optimality alignment. So your system is just like, it has a different goal, but it's like not yet so good at optimizing for that goal. And when you're kind of bad at optimizing for that goal, it looks like it's optimizing for the thing that the base optimizer wants. So proxy alignment, approximate alignment, and sub-optimality alignment. And pseudo alignment is like the general thing where like it looks like you're inner aligned, but you're not really. So one thing I kind of wanted to know is how much of the space of pseudo alignment cases do you think that list of three options covers?
Yeah, so maybe it's worth also first. There's a lot of terminology being thrown around, so I'll just try to clarify some of these things.
All right.
So the base objective, we sort of mean basically the loss function.
Yep.
So we're trying to understand. We have some machine learning system. We have some loss function. We'll call this the base objective, or a reward function, whatever. We'll call this the base objective.
Yep.
We're training a model according to that base objective. But the actual MESA objective that it might learn might be different, because there might be many different MESA objectives which perform very well on the training distribution, but which are sort of have different properties off distribution, like going to the green arrow versus getting to the end of the maze. And we're trying to catalog the sort of ways in which the sort of model can be pseudo-aligned, which is sort of, it looks like it's aligned on distribution, in the same way that getting to the end of the maze and getting to the green arrow both sort of look like they're aligned on the training distribution. But when you move them off distribution, they no longer are aligned, because one of them does one thing and one of them does the other thing. And so this is sort of the general category of pseudo-alignment. And so so we try to categorize them, and we have this sort of some sort of possible categories of the sort of proxy alignment. Proxy alignment being the sort of main one that we sort of I think about the most, and the paper talks about the most. Approximate alignment and sub-optimality alignment also being sort of other possible examples. In terms of the extent to which I think this sort of covers the full space, I don't know. I think it's sort of, a lot of this is sort of tricky because it depends on exactly how you're sort of defining these things and understanding like what counts as a MESA optimizer, what doesn't count as a MESA optimizer. Because you could certainly imagine situations in which a thing is like, does something bad off distribution, but not necessarily because it learned some incorrect objective or something. And sub-optimality alignment even is sort of already sort of touching on that, because sub-optimality alignment is thinking about a situation in which the model has a sort of defect in its optimization process that causes it to look aligned, such that if that defect were sort of to be fixed, it would no longer look aligned. And so you're sort of already sort of starting to touch on some of the situations which, well, maybe the reason that it looks aligned is because of some weird interaction between the sort of objective and the optimization process, similar to sort of your example of the way in which it maximizes is actually it minimizes or something. I don't know. I think there are other sort of possibilities out there than just those three. I think that we don't sort of claim to have an exhaustive characterization. Um, and one of the things also that I should note is I do like have, I don't know, I've like done some, there's one post that I made later on after sort of writing the paper that clarifies and sort of expands upon this sort of analysis a little bit, which brings up the case of, for example, suboptimality deceptive alignment, which would be a situation in which the sort of model should act deceptively, but hasn't sort of realized that it should act deceptively yet, because it's like not very good at thinking about what it's supposed to be doing. But then later it realizes it should act deceptively and starts acting deceptively. Which is sort of an interesting case where it's like sort of suboptimality alignment, sort of deceptive alignment. And so that's for example another sort of
So
case.
if it's not, so if it's suboptimal and it's not active and it's not acting deceptively, does that mean that you notice that it's optimizing for a thing that it shouldn't be optimizing for, and like just because it does a different thing that it's supposed to do, and then great?
Yes, the suboptimality alignment is a little bit tricky. The point that we're trying to make is it's not that it's like suboptimal at optimizing the thing it's supposed to be optimizing for, such that it looks like it's doing the right thing, right? So,
Yep.
for example,
and simultaneously suboptimal at being deceptive in your suboptimality deceptive alignment.
Well, if it, yeah, I mean, or it's suboptimal in the sense that it's like it hasn't realized that it shouldn't be deceptive, and maybe if it had realized it would be deceptive, then like it might start sort of doing bad things and looking because it like tries to defect against you or something at some point. It would be sort of no longer actually aligned. Whereas like if it never figures out that it's supposed to be deceptive, then maybe it like just looks totally aligned basically for most of the time.
Okay.
I know. So there certainly are other sort of possible cases than just those. I think that it's not sort of exhaustive. Like I mentioned, I don't know. I don't remember exactly what the title of it. I think it's More Variations on Pseudo Alignment is the one that I'm referencing. That talks about some of these other sort of possibilities. And there are others. I don't think that's exhaustive, but it is sort of I don't know, some of the sort of possible ways in which this can fail.
Do you think it covers as much as half of the space? Those main three?
Yeah, I do. I think actually what I would say is I think proxy alignment alone covers like half the space. Because I basically expect, like, I think proxy alignment really is like the central example in like a meaningful way, and that like I think it captures like most of the space, and the others are sort of looking mostly at sort of edge cases.
Okay, so a question I have about proxy alignment and really about all of these inner alignment failures. It seems like your story for why they happen is essentially some kind of unidentifiability, right? You know, your proxy misaligned because you know, you have a vacuum. The base objective is to have that vacuum like clean your floors, and somehow the mesa objective is instead to get a lot of dust inside the vacuum, and that you normally get from floors, but you know, you could imagine other ways of getting it. And the reason you get this alignment failure is that, like, well, on distribution, you just like there was only one. Whenever you had dust inside you, it was because you cleaned up the floor. So what I'm wondering is, as we train better AIs, you know, as that have more capacity, they're smarter in some sense, on more rich data sets. So whenever there are like imperfect sort of probabilistic causal relationships, we like find these edge cases and we can select on them. And you know, these data sets have like more features and they just have more information in it. Should that make us less worried about inner alignment failures because we're reducing the degree to which there's these unidentifiability problems?
So this is a great question. So I think a lot of this comes back to what we were talking about previously also about adversarial training. So I think that there's a couple of things going on here. So first, unidentifiability is really not the only way in which this can happen. So unidentifiability is sort of required at zero training error. If we're imagining a situation where we have zero training error, it perfectly fits the training data, then yeah, in some sense, it has to be, if it's sort of misaligned, it has to be because of unidentifiability. But in practice, in many situations, we don't train to zero training error. We have these really complex data sets that like are very difficult to fit completely. And you train sort of far before zero training error. And in that situation, it's not just unidentifiability. And in fact, you can end up in a situation where the inductive biases can be sort of stronger in some sense than the sort of the training data. And this is sort of, if you think about avoiding overfit. If you train sort of too far on the training data, sort of perfectly fit, you sort of overfit the training data because now you've trained a function that sort of just perfectly goes through all of it. There's double descent, like we were talking about previously, to sort of calls some of this into question. But if you just think about stopping exactly at zero training error, this is sort of a problem. But if you think about instead, sort of not overfitting and sort of training a sort of model which is able to sort of fit a bunch of the data, but not all of the data, but you stop such that you sort of still have a strong influence of your inductive biases. on like the actual sort of thing that you end up with, then you're in a situation where it's not just about undeniability. It's also about like you might end up with a sort of model that is much simpler than the model that actually fits the data perfectly. But because it's much simpler, it actually has better generalization performance. But because it's much simpler and doesn't fit the data, it might also have sort of these sort of a very simple proxy, and that simple proxy is sort of not necessarily exactly the thing that you want. An analogy here that sort of is from the paper that I think is sort of useful to think about is imagine a situation. We talked previously about sort of the sort of example of sort of humans being sort of trained by evolution. And I think this example, there's sort of, I don't necessarily love this example, but it is sort of, in some sense, the only sort of one we have to go off. And so if you think about a situation, what actually happened with humans in evolution? Well, evolution is trying to sort of train humans in some sense to sort of, maximize genetic fitness, to, reproduce and to like produce, continue, carry their DNA on, down into future generations. But in fact, this is not the thing which humans actually care about. We care about all these sorts of other things like food and mating and like all of these sorts of other proxies, basically, for the actual thing of getting our DNA into future generations. And I think this makes sense. And it makes sense because, well, if you imagine like a situation where like sort of an alternative human that like actually cared about DNA or whatever, it would just be really hard for this human. Because first of all, this human has to do a really complex optimization procedure. They have to like first figure out what DNA is and understand it. They have to have this really complex high-level world model to understand DNA and to understand like that they care about this DNA being passed into the future generations or something. And they have to do this really complex optimization. Like if I stub my toe or whatever, I know that that's bad because they get a pain response. Whereas if a human in this alternative world stubs their toe, they have to like deduce the fact that like stubbing your toe is bad because it like means that toes are actually useful for being able to like run around and do stuff, and like that's useful for being able to get food and being able to like attract a mate, and like therefore because of like having a sort of stubbed toe, like I'm not gonna be able to do those things as effectively, and so I should avoid stubbing my toe. But that's a really complex optimization process that like requires like a lot more sort of requires a lot more compute. It requires it could potentially it's much more complicated because like specifying DNA in terms of your input data is really hard. And so we might expect that a similar thing will happen to neural networks, to models, where even if you're in a situation where you could theoretically learn this sort of perfect proxy to like actually care about DNA or whatever, you'll instead learn simpler, easier to compute proxies, because those simpler, easier to compute proxies are actually they're better because if they're easier to sort of actually produce actions based on those proxies, you don't have to do some complex optimization process based on the real sort of correct thing. They're easier to sort of specify in terms of your input data, so they're easier to sort of compute and figure out what's going on with them. They don't require as much sort of description length and as much sort of explicit encoding, because you don't have to sort of encode this complex world model about like what is DNA and how does all of this sort of work. You just have to encode like, if you get a pain signal, don't do that. And so in some sense, I think we should expect sort of similar things to happen, where like even if you're in a situation where you're not sort of where like you're training on this sort of really rich detailed environment where like you might expect it to be the case that like the only thing which will work is the thing which is actually the correct proxy. In fact, a lot of incorrect proxies can be better at achieving the thing that you want because they're simpler, because they're faster, because they're easier. And so we might expect even in that sort of situation to end up with sort of simpler, easier proxies.
Yeah, and I guess that's interesting because it's sort of, well, like when I'm thinking about that, it seems like there's this trade-off of like if like you could imagine a world where evolution or the anthropomorphic god of evolution or whatever put like this it really did say, Daniel, the thing you're going to care about is like gene alleles, like the allele frequency of I bet I'm using the wrong terminology, but how much my genes are in the population. Also, Daniel, stubbing your toe, bad, like it doesn't help with that. Like you should pain typically like not good for this. But like what you really care about is your genes being propagated. And in that case, I really presumably like I'm going to basically like behave fine. And when these things are going to diverge, hopefully I eventually figure it out. But there's this problem. I guess there are two problems. Firstly, like then it's like a lot more description length because you have to preload all of this information. And secondly, there's this issue where like, well, when I'm kind of dumb, the bit of me that's saying like, well, what you actually care about is propagating your genes. that's not actually influencing my behavior in any way, because I'm just like acting on the proxies anyway, because I know they're proxies. So like if there's some kind of pressure to like it seems like that bit is just going to be like totally unmoored and like might randomly drift, or maybe get pruned away because it's just like not influencing my behavior.
Yeah, I think that's basically exactly what I would say. I agree with that.
Cool.
On both points.
All right. Another thing, this question is kind of long, and it only eventually gets to being about inner alignment. So I'm sorry, listeners, but we're going to get there. So there's this argument in the paper which basically says that if you're training a system for a diverse set of tasks, you want to expend most of your optimization online, like once the task is known. You don't want to do like a bunch of your optimization power in like generating this system and then pre-computing like, okay, I'm going to figure out the policy for this type of task and pre-compute like this type of task. You just want to do that like optimization once you know the task, so that you can only do it for the thing that's actually useful. And this reminded me a lot of Eric Drexler's comprehensive AI services, or CAIS model, where you just like, instead of having an AGI, you just like, there are a bunch of tasks you want to be done, and you just have a bunch of like AIs that are like made for each type of task. And when you have a task, you like select the appropriate AI. So I'm wondering, like, my first question is, does this argument like kind of reinforce or like is this an argument for the idea of doing something like CAIS instead of creating this like single unified AGI?
Yeah, so I think it gets a little bit more complicated when you're thinking about like how things play out like on a sort of strategic landscape. So there might be many reasons for why you want to build like one AI system and then like, for example, fine tune that AI system on many different tasks, as opposed to like independently training many different AI systems. Because if you independently train many different AI systems, you have to like expend a bunch of training compute to do each one. Whereas if you like train one and then fine tune it, you like maybe have to do like less training compute because you just do it like you a lot of the sort of overlap you get to do only once. I think in that sense, and I think that sort of does the sort of argument I just made sort of does parallel the sort of argument we make in the paper, where it's like, well, there's a lot of things you only want to do once, like the building of the optimization machinery. You only want to do once. You don't want to have to sort of figure out how to optimize every single time. But the like explicit sort of what task you're doing, the locating yourself in the environment, locating the specific task that you're being asked to do, is the sort of thing that which you sort of want to do online. Because it's just really hard to pre-compute that if you're in an environment where you have to have like massive sort of possible divergence and like what task you might be presented at any different point. Uh, and so there's a sort of similarity there where like it sort of suggests that like in a case sort of style world, you might also want like a situation where like you have like one AI which sort of knows how to do optimization, and then you fine tune it for many different sort of possible tasks. You can, and it doesn't necessarily have to be like actual fine tuning. You can also think about something like GPT-3, sort of with the OpenAI API, where people have been able to sort of locate specific tasks just via prompts. So you can imagine something like that also being a situation where like you have a bunch of different tasks. You train one model which has a bunch of general purpose machinery, and then a bunch of different sort of ability to like locate specific tasks. I think any of these sort of possible scenarios, including the sort of you just train many different AIs for sort of very different tasks because you really need fundamentally different machinery, are plausible. And I think risk limit optimization basically applies in all these situations. I mean, like whenever you're training a model, like you have to worry that you might be training a model which is sort of learning an objective which is different from the loss function you're training under, regardless of whether you're sort of training one model and then sort of fine tuning a bunch of times, or training many different models, or whatever sort of situation you're in.
Yeah, so the reason I bring it up is that if I think about this case scenario where, like, say, you the way you do your optimization online is you want to be able to deal with like these 50 environments. So you train, maybe like pre-train one system, but you fine tune like all 50 different systems. You have different AIs, and then once you realize you're in one of the scenarios, you deploy the appropriate AI. Say, to me, so that seems like a situation where instead of this inner alignment problem, where I had this, you have this system that's like training to be a Mesa optimizer, and it needed to like spend a bunch of time doing a lot of computation, to like figure out what worlds it's in and figure out an appropriate plan. It seems like in this case world, you just have like you want to train this AI. And the thing that like the optimization that like in the unified AGI world would have been done like inside the thing during inference, you get to do. So you can create a this machine learner that doesn't have that much inference time. You can make it like not be an optimizer, so maybe you don't have to worry about these inner alignment problems. And then it seems like what Case is doing is it's saying, well, I'm going to trade your inner alignment problem for an outer alignment problem of, getting the base objective of this machine learning system to be what you actually want to happen. And also you get to be assisted by like some AIs maybe that you like already trained, potentially to help you with this task. So I'm wondering, first, do you think that's an accurate description? And secondly, if that's the trade, do you think that's a trade worth making?
Yeah, so I guess I don't fully buy that story.
Hmm.
So I think that if you think about like a case setup, I don't think so. So I guess you could imagine one situation like what you were describing, where you trained a bunch of different AIs, and then you have like maybe a human that tries to switch between those AIs. I think that first of all, I think this runs into like competitiveness issues. I think there's a question of like how good are humans at figuring out like what the sort of what the correct strategy is to deploy in this situation. In some sense, that might be the sort of thing which we want AIs to be able to do for us.
The human could be assisted by an AI.
Yeah, you could even be assisted by an AI, but then you like also have the problem of is that AI doing the right thing? And in many ways, I think that in each of these individual situations, like I have a bunch of AIs that are trained in all these different ways in different environments, and I have maybe another AI which is also trained to assist me in figuring out what AI I should use. Each one of these individual AIs has an inner alignment problem associated with it. Now, might that inner alignment problem be easier because they're trained on more restricted tasks? In some sense, yes. I think that if you train on a more restricted task, you're less likely to end up with, search is less valuable because you sort of have this sort of less generality. But if at the end of the day you want to be able to solve really general tasks, like the generality still has to exist like somewhere. And I still expect you're going to have lots of models which are trained in like relatively general environments, such that you're going to like, search is going to be incentivized. You're going to have, some models which have sort of, MACE objectives. And in some sense, it also makes sort of part of the control problem harder because you have all of these sort of potentially different MACE objectives and different models, and it might be harder to sort of analyze exactly sort of what's going on. It might be easier because they're less likely to have MACE objectives, or it might be easier because it's harder for them to sort of coordinate because they don't share the exact same architecture and MACE objective potentially. So I'm not exactly sure the extent to which this is like a better setup or a worse setup, but I do think that it's a situation where like I don't think that like you're sort of trading making the inner alignment problem go away or turning it into a different problem. It still exists, I think, in basically the same form. It's just like you have an inner alignment problem for each one of the different systems that you're training, because that system could itself develop, a search process or an objective that is different from the loss function that you're actually trying to get it to pursue. And I guess, like, if you think about a situation, I think there's like so much generality in the world that like, maybe we're in a situation where like, let's say I train like, 10,000 models. I reduced the like total generality in the world by like, some number of bits, whatever, 10 to the, 3, like 3 orders of magnitude or whatever, right? What did I say? 10,000 orders of magnitude, whatever. Some number of orders of magnitude, right? Is the extent to which I've reduced the total space of generality. But the world is just so general that like even if I train 10,000 different systems, like the amount of sort of possible space that I need to cover if I want to be able to do all of this various different things in the world, to respond to like various different possible situations, there's still so much generality that I still think you're basically going to need search. Like you just haven't reduced the space, like the sort of the like amount of which you've reduced the space by cutting it down. By like having multiple models is just dwarfed by the size of the space in general, such that you're still going to need to have models which are capable of dealing with large generality and being able to respond to many different possible situations. Now, you could also imagine like, if you're trying to do an alternative situation where like it's case, but it's also you're trying to do case like microscope AI or STEM AI, where you're like explicitly not trying to solve all these sorts of general purpose situations. Maybe things are different in that situation. But I think certainly if you want to do something like case, like you're describing, you have a bunch of different models for different situations, and you want to be able to solve like, AI CEOs or something. It's just the problem is so general that like you just there's still enough generality. I think that you're going to need search. You're going to need like optimization.
Yeah, I guess so. I think I'm convinced by the idea that there's just like so many situations in the world that like you can't like manually like train a thing for each situation. I do want to push back a little bit on the and actually like that thing I'm conceding is just enough for the argument. But anyway, I do want to push back on the argument that that you still have this inner alignment problem. which is that like the thing in inner alignment problem is, at least in the context of this paper, is it's when you have a mesa optimizer, and that mesa optimizer has a mesa objective that is not the base objective. And it seems like in the case where you have these like not very general systems, you have the option of training things that just don't use a bunch of computation online, like don't use a bunch of computation at inference time, because they don't have to figure out what task they're in because they're already in one, and instead they can just like be a controller, you know. So these things aren't mesa optimizers, and therefore they don't have a mesa objective, and therefore there is no inner alignment problem. Now maybe there's like the analog of the inner alignment, there's the like compiled inner alignment problem, but that's what I was trying to get at.
Yeah, so I guess the point that I'm trying to make is that even in a situation where like you're like, oh, it already knows what task it needs to do because we trained the thing for a specific task, is that if you're splitting the entirety of like a really complex problem into only 10,000 tasks
Yep.
or whatever, only 1,000 tasks, like that each individual task is still going to have so much generality that you're gonna. I think you'll need search, you'll need base optimization, you'll need a lot of inference time compute, even to solve it at that level of granularity.
Okay.
The point that I'm making is that just like I think that the problem itself requires is like, you know, if you're trying to solve really complex general problems, there's enough sort of generality there that even if you're sort of going down to the level of granularity, which is like 1,000 times reduced, there's still enough granularity. You'll probably need search, or probably want you'll still probably get base optimizers there. You're going to need a lot of inference time compute, et cetera, et cetera.
Okay, that makes sense. I want to talk a little bit now about deceptive alignment. So deceptive alignment is this thing you mentioned in the paper, where your mesa optimizer has a different goal than, and we've talked about this before, but to recap, your mesa optimizer has a different mesa objective than what the base objective is. And furthermore, like your mesa optimizer is still being trained, and its mesa objective compares like it cares about what happens like after gradient updates. So it cares about steering the direction of gradient updates. So therefore, in situations where the mesa objective and the base objective might come apart, if you're deceptively aligned, your mesa optimizer picks the thing that the base objective wants, so that its mesa objective doesn't get optimized away, so that, you know, one day it can like live free and no longer have to be subject to gradient updates, and then, you know, pursue its mesa objective. Correct me if that's wrong.
I think that's like a pretty reasonable description of what's going on.
Yeah. So the paper devotes a fair bit of space to this, and I'm wondering, like, well, like it mostly devotes space to what happens if you get deceptive alignment. And what I'm kind of interested in, and I don't really understand, is how this occurs during training. So at what point do you get an objective that cares about what happens like after episodes, you know, after gradients or updates, after gradient updates are applied? Like, how does that end up getting selected for?
Yeah. So this is a really good question, and it's a complicated one. And so we do talk about this in the paper, and a good deal. I think there's also a lot of other discussion in other places. So like one thing just to point out, so let's see, Mark Zhu has this post on alignment forum, does SGD produce deceptive alignment, which I think is a really good starting point. Also, I worked with him a bunch on sort of putting together a lot of the arguments for this in that place. So I think that's a good place to look. But I'll try to sort of talk through some of the ways in which I sort of view this.
Okay.
So I think that we sort of in the paper we sort of have this sort of following story, and telling stories about gradient descent is hard, and it's the sort of thing where like you should expect to be wrong in a lot of cases. And so I'm going to tell a story, but like I don't necessarily think that this is precisely the sort of story that you would end up with. But I think there's sort of general purpose arguments there's sort of general arguments that you can make for why this might be likely, why it might not be likely. And I think that like telling stories is helpful for trying to understand like what a setup might be like in which you would get this. So here's the story I'm going to tell. So we have a proxy aligned mesa optimizer. I think that basically this is sort of where you start, because, you know, if we're thinking about, you know, all of the sort of arguments I made previously, thinking about things like, you know, humans, having a pain response rather than a sort of, you know, caring about DNA, you're going to start with some proxy, simple, fast proxies. You know, but maybe you do a bunch of adversarial training. Maybe you do a bunch of trying to sort of, train on all of the sort of different situations. You really force it to go to zero training error to really understand everything that's happening, to have to sort of have a perfect version of the base objective. What happens in this situation? Well, at some point, you know, we'll say it has to learn the base objective, it has to know what the base objective is and be able to, you know, to like act directly according to that base objective. But there's multiple ways in which a model can learn what the base objective is. So one way in which it can sort of learn what the base objective is, well, it has the base objective directly hard-coded into it via gradient descent. So it has some proxy objective, and gradient descent sort of tinkers with that objective and keeps sort of like encoding into it sort of more and more detail to like what the correct thing is. That's one way. We call that in the paper internalization. There's another way, which is it can learn what the base objective is via its input data. So rather than via the gradient descent update steps being the thing which sort of encodes the objective into it, it could, maybe you're trying to train it to do language modeling, predict what a human would do, and it just reads a bunch about humans and how they work. Or maybe you're training it to do value learning and try to sort of do, optimize for human values, and it reads, Wikipedia page on ethics, and it tries to really understand human values. And so it gets a bunch of information about the objective that you're training it on through its input data. It gets a bunch of information about like the thing that you're trying to get it to do, just because if you're GPT-3 style, whatever, you're training it on a huge, you can imagine training on a huge corpus of data. It has a whole bunch of information. And a lot of that information is just, whatever you're training it on is probably going to be somewhere there's going to be information about that thing that you're training it on in that input data. And so it can also just figure out what the objective is by looking at that input data. But then there's a question, which is, well, so let's say the model, it's doing a bunch of world modeling, it's trying to understand the world, and so it's produced, an internal model that includes what the like correct base objective, but it doesn't know that's the correct base objective. It's not trying to optimize for that. It's just trying to optimize for its proxy. It'd be really nice from the perspective of gradient descent, from the perspective of the training process, if it, instead of optimizing for its proxy, started optimizing for that thing which is encoded in the world model, started optimizing for its like description, its like better understanding of the base objective. And so there's a question, how does gradient descent, how does the training process modify the model to start optimizing for that thing encoded in its world model? And fundamentally in the paper, we sort of analyze two ways. One of which is sort of we call corrigible alignment, which is, well, its objective could change into a sort of pointer to that thing in the world model. And another way is sort of deceptive alignment, which is it could realize that as an instrumental goal for optimizing its proxy, it should be trying to optimize for this thing because it realizes that that's the base objective that it's being trained under. And so then there's a question, and so we end up with sort of three ways in which it could learn the base objective: internalization, corrigibility, and deception. And then there's the sort of question that we ask, which is, well, how likely are these different things to occur? How well do they perform on things like simplicity? Are they like, how well do these measures perform? So one sort of thing that I'll start with, and this is an analogy from Buck-Schligeris, which is sort of a counting argument, which is just like, well, let's just start with the question, how many models are there that fall into each one of these categories? And I think the answer is, well, there's a lot more deceptive models. And so here's the analogy to sort of think about why that's the case. So we can imagine a situation where you have this sort of Christian God is like trying to select humans according to the extent to which they sort of align with the Bible. And you can imagine three sort of different humans that might sort of fall into this category. So one of which would be Jesus Christ, who is just like has the exact same objective as God, because
in Christianity, I believe Jesus Christ is not totally a human, right?
Sure, I agree with that. But let's sort of set that aside and imagine that Jesus Christ is like a possible sort of option here that God is sort of considering between. And Jesus Christ has the exact same objective as God does because, whatever. And then you have another sort of example, which is, let's say, Martin Luther. And Martin Luther is like, I'm going to look at the Bible and figure out exactly what the Bible says. And like try to do that as like effectively as possible. And then you have Blaise Pascal, and Blaise Pascal is like, I don't care about the Bible, I don't care about God, but I know that there is a God, and that God is going to like select me according to whether I care about the Bible. So I'm going to like care about the Bible. And these sorts of three people match on to pretty closely match on to the sort of three sort of scenarios that I described. So Jesus Christ is internalization, Martin Luther would be sort of corrigibility, and Blaise Pascal would be deception. And the question is, how many Blaise Pascals are there? How many Martin Luthers are there? And how many Jesus Christs are there? And I think the sort of initial response would be, well, there's only one sort of Jesus Christ because it has to like explicitly encode the entirety of the objective. There might be multiple Martin Luthers because, pointing in, there might be sort of some sort of basin of, corrigibility. It might be the case that like, if you get your pointer slightly wrong, you can still like correct it by figuring out like what the Bible says about what your pointer should be. But you still basically have to have exactly the correct pointer to the Bible. And like believe that the Bible is the thing you should be following. But there's a lot of Blaise Pascals, because Blaise Pascal can have any objective, essentially. As long as Blaise Pascal is aware of the fact that they're an optimization process, whatever their objective is, they're going to try to sort of change it to, be the one that is according to the Bible or whatever. And so there's this simple counting argument, which is, well, it just seems like there's a lot more deceptive models than the others. And so just as a very sort of naive prior, it seems like we should expect deception. But we can go further than that, and we can try to ask further questions of like simplicity and like, how likely would this actually be to occur in a gradient descent process? So it seems like...
So before we get to those arguments, so you're right that the paper does devote a fair bit of space to like, okay, suppose you have a proxy, your proxy aligned, and your proxy, extends across gradient updates. And, then you learn about the base objective. And I think there's like a decent story in the paper that people can read for like how that happens once you have this proxy that extends past gradient updates. And I think my initial question, like to me, the thing, maybe listeners are different, but to me, the thing that seems most implausible about this story is that gradient descent produces this kind of proxy. Because like that kind of proxy is not like when the gradient is applied, the thing evaluating the gradient doesn't know whether the objective that extends past when the gradient applies was met or not, because like it hasn't happened yet. So how do we... The thing that confuses me the most is how do you ever get a situation where your system cares about what happens after the gradients are applied?
Yes, that's a great question. And in fact, this is actually really close to a lot of the research that I'm currently doing, trying to understand precisely the situations in which you get sort of these cross-episodic objectives. And other situations, you can produce sort of myopic objectives instead. So I think the way to think about this is that fundamentally it's a generalization question, because you're correct that when you're doing training, it doesn't understand that, there's like potentially, multiple episodes in your reinforcement learning setting. So it doesn't know about the multiple episodes. And so it learns an objective that isn't really sort of in terms of those multiple episodes. But let's say it does discover the existence of those multiple episodes. The question that we're asking is, how does it generalize? How does it generalize in terms of caring about those multiple episodes or not caring about those multiple episodes? It learns some understanding of an objective, some understanding of what it's supposed to be, what sort of proxy it's trying to fulfill. And that proxy, how once it discovers that these other episodes exist, does it think that does it think that its proxy also exists there? Does it care about its proxy in those situations also or not? And that's sort of the question we're answering, this sort of generalization question. And I think that by default, we should expect it to generalize such that, here's a very simple intuitive argument is, if I train a model and it's trying to find all the red things it can, and then suddenly it discovers that there are way more red things in the world than it previously thought, because there's also all of these red things in these other episodes. I think that by default, you should basically expect it's going to try to get those other red things too. That like it would require an additional sort of distinction in the model sort of understanding of the world to believe that, only these red things are the ones that matter, not those red things. And that sort of distinction, I think, is not the sort of distinction that you would be... gradient descent sort of has no reason to put that distinction in the model, because like you were saying, in the training environment where it doesn't understand that there are these multiple episodes, whether it has or does not have that distinction is completely irrelevant. It only matters when it ends up in a generalization situation where it understands that there are multiple episodes and is trying to figure out whether it cares about them or not. And in that situation, I expect that this sort of distinction would be lacking. That it would sort of be like, well, there are red things there too, so I'll just care about those red things also. Now, this is a very sort of hand-wavy argument. And it's certainly like, I think a really big open question. And in fact, I think it's one of the places in which I feel like we have the most opportunity potentially to intervene, which is sort of why I was talking about one of the ways in which it's sort of a place where I focus a lot of my research, because it seems like if we are trying to not produce deceptively aligned base optimizers, then one of the ways in which we might be able to intervene on this story would be to prevent it from developing an objective which cares about multiple episodes and instead ensure that it develops a sort of myopic objective. Now, there's a lot of problems that come into play when you start thinking about that. And we can go into that. But I think just sort of on a surface level, the point is that, well, just by default, it's certainly, despite the fact that you might have a myopic training setup, whether you actually end up with a myopic objective is very unclear. And it seems like myopic objectives might be more complicated because they might require this sort of additional sort of restriction of, not just like objective everywhere, but actually objective only here. And that sort of might require additional description length that might make it sort of more complex. But certainly it's not the case that we really understand exactly what will happen. And sort of one of the interesting things that's happening here is it's sort of breaking sort of the assumptions of reinforcement learning, where when we sort of a lot of times when we do reinforcement learning, we assume that the sort of episodes are IID, that they're sort of independent, that that the model, we just totally resample the episodes every time, and there's no sort of way for it to sort of influence across episodes. But this sort of problem starts to occur as soon as you start entering situations where it does have the ability to influence across episodes.
Such as online learning, like we mentioned at the start, which is, a common, like often I think when you're thinking about how are we going to get like really powerful AIs that work in reality, it's like, yeah, we're going to do online learning.
Precisely, yeah. And so if you think about, for example, an online learning setup, maybe you're imagining, something like a recommendation system. So it's trying to sort of recommend you YouTube videos or something. One of the things that can happen in this sort of a setup is that, well, it can try to change the distribution to make its task easier in the future. If it tries to give you videos which will change your views in a particular way, such that it's easier to satisfy your views in the future, that's a sort of non-myopia that is sort of could be incentivized just by the fact that you're doing this sort of online learning over many sort of steps. And if you think about something, especially what can happen in this sort of situation is, let's say I have a sort of, or another situation this can happen is, let's say I'm just trying to sort of train a model to sort of satisfy, humans' preferences or whatever. It can try to modify the human's preferences to be easier to satisfy. And that's a sort of another way of which sort of this sort of non-myopia could be manifest, where it tries to take some action in one episode to make humans' preferences different, so then future episodes they'll be easier to satisfy. And so there are a lot of these sorts of non-myopia problems, and not only. So I was making an argument earlier that it seems like non-myopia might just be simpler. But there's also a lot of things that we do that actually explicitly incentivize it. So if you think about something like population-based training, population-based training is a technique where what you do is you basically create a sort of population of models, and then you sort of evolve those models over time. You're changing their parameters around and moving sort of changing their hyperparameters and stuff to sort of make it so that they have the sort of best performance over many episodes. But as soon as you're doing that, as soon as you're trying to select for models which have the best performance over multiple episodes, you're selecting for models which do things like change the human's preferences such that in the next episode they're easier to satisfy, or recommendation systems which like try to change you such that you'll be easier to sort of give things to in the future. And this is the sort of thing that actually can happen a lot. So David Kruger and others have a paper that talks about this, where they sort of talk about these sort of as hidden incentives for sort of distributional shift, or sort of auto-induced distributional shift, where the sort of model can itself you can have setups like population-based training where the model sort of is directly incentivized to sort of change its own distribution in this sort of non-myopic way. And so in some ways, there's sort of like two things going on here. There's like, it seems like even if you don't do any of this sort of population-based training stuff, the sort of non-myopia might just be simpler. But also there's a lot of the techniques that we do that, because they implicitly assume this sort of Iid assumption that's in fact not always the case, they sort of implicitly can be incentivizing for non-myopia in ways that we might not want.
Okay. So I have a few questions about how I should think about the paper. So the first one is, like most of the arguments in this paper are kind of informal, right? There's very few mathematical proofs. You don't have experiments on MNIST, the gold standard in ML. So how confident are you that the arguments in the paper are correct? And separately, how confident do you think readers of the paper should be that the arguments in the paper are correct?
That's a great question. Yeah. So I think it really varies from argument to argument. So I think there's like a lot of things that we say that I feel pretty confident in. Things like, I feel pretty confident that like search is going to be like a component of models. I feel pretty confident that like, you will get simple, faster proxies. Some of the sort of more complex stories that we tell, I think, are sort of less sort of, compelling. Things that I feel like are somewhat less compelling, like, we have the description of a MESA optimizer as having this really coherent optimization process and really coherent objective. I think that like, I do expect search to the extent to which I expect a really coherent objective and a really coherent optimization process. I'm not sure. I think that's certainly a sort of limitation of our analysis. Also, some of the stories I was talking about deception, I think, I do think that like there's a strong prior that like should like, be like, it seems like deception is likely, but we don't understand it, fully enough. We don't have like examples of it happening, for example. And so it's certainly like something where we're sort of more uncertain. So I do think it sort of varies. I think that there's sort of some arguments that we make that I feel relatively confident in, something I feel relatively less confident in. I do think, I mean, we make an attempt to really sort of look at, what is our knowledge of, machine learning inductive biases? What is our understanding of, the extent to which, certain things would be incentivized over other things, and try to use that knowledge to like come to the best conclusions that we can. But of course, that's also limited by the extent to which of our knowledge. Our understanding of inductive biases is relatively limited. We don't fully understand exactly what neural networks are doing internally. And so there are fundamental limitations to how good our analysis can be and how accurate it can be. But I do think that in terms of this is our best guess currently, I feel like is how I would sort of think of the paper.
Okay. And I guess sort of a related question. I think my understanding is like a big motivation to write this paper is like, just generally being worried about like really dangerous outcomes from AI and thinking about how we can avert them. Is that fair to say?
Yeah, I mean, certainly the motivation for the paper is we think that the sort of situation in which you have a MESA optimizer that is optimizing for an incorrect objective is like quite dangerous, and that this is like the central motivation. And there's many reasons why this might be quite dangerous. But the sort of simple argument is, well, if you have a thing which is really competently optimizing for something which you did not tell us to optimize for, that's not a good position to be in.
So I guess my question is, what out of all the ways that we could have like really terrible outcomes from AI, what proportion of them do you think do come from inner alignment failures?
That's a good question. Yeah. So this is tricky. I mean, any sort of number that I give you isn't necessarily, going to be super well informed. I don't have like, a really clear sort of an analysis behind any number that I give you. My expectation is that most of the worst problems, sort of the majority of existential risk from AI comes from inner alignment and mostly comes from deceptive alignment, would be my personal guess. And some of the reasons for that are, well, I think that like there's a question of what sorts of things will we be able to correct for, and what sorts of things will we not be able to correct for. And I think that there's a sense in which, if you think about the sort of the thing we're trying to avoid is these unrecoverable failures, situations in which our feedback mechanisms are not capable of responding to what's happening. And I think that sort of deception, for example, is particularly bad on this, especially if you have a situation where because the model basically looks like it's fine until it realizes that it will be able to overcome your feedback mechanisms, in which case it no longer looks fine. And that's really bad from the perspective of being able to correct things by feedback, because it means you only see the problem at the point where you can no longer correct it. And so those sorts of things are why sort of lead me into the direction of thinking that things like deceptive alignment are likely to be a large source of the existential risk. I also think that just I think that there's certainly a lot of risk also just coming from standard proxy alignment situations, as well as relatively straightforward outer alignment problems. I am sort of, relatively more optimistic about outer alignment because I feel like we have better approaches to address outer alignment. I think that things like Paul Cristiano's amplification, as well as his learning the prior approach, Jeffrey Irving's debate, I think that there exist a lot of approaches out there which I think have made significant progress on outer alignment, even if they don't fully solve outer alignment. Whereas I feel like our progress on inner alignment is sort of less meaningful, and I expect that to sort of continue, such that I'm more worried about inner alignment problems.
So I guess this gets to a question I have. So one thing I'm kind of thinking about is okay, what do we do about this? But before I do that, in military theory, there's this idea called the OODA loop. OODA is short for OODA. It's observe, orient, decide, and act, right? And the idea is if you're a fighter pilot and you want to know what to do, first you have to observe your surroundings. You have to orient to decide, to think about, okay, what are the problems here? What am I trying to do? You have to decide on an action, and then you have to act. And, the idea of the OODA loop is you want to complete your OODA loop, and you want to not have the person you want to shoot out of the sky complete their OODA loop. So instead of asking you what we're going to do about it and jumping straight to they, first I want to check, where in the OODA loop do you think we are in terms of inner alignment problems?
Yeah, so it's a little bit tricky. So in some sense, there's first of all, there's a view in which we aren't even at observe yet, because we don't even have really good empirical examples of this sort of thing happening. We have examples of machine learning failing, but we don't have examples of is there an optimizer in there? Does it have an objective? Did it learn something? We don't even know. And so in some sense, we aren't even at observe. But we do have some evidence, right? So, the paper looks at lots of different things and tries to understand, some of what we do understand about machine learning systems and how they work. So in some sense, we have observed some things. And I certainly don't think that, and so in that sense, I would say the paper is sort of more at orient. The paper doesn't, risk and optimization doesn't come to a conclusion about this is the like correct way to resolve the problem. It's more just like trying to understand the problem based on the things that we have observed so far. There are other things that I've written that are more sort of at the like decide stage, but are still, I don't know, still mostly at the orient stage. I mean, so like stuff like my post on relaxed adversarial training for inner alignment is closer to the decide stage because it's investigating a particular approach, but it's still more just like let's orient and try to understand this approach because it's like there's still so many open problems to be solved. So I think we're still relatively early in the process for sure.
Do you think that it's a problem that we're doing all this orientation before the observation, which is like, I guess, the opposite of what, if you take OODA loop seriously, it's like the opposite order that you're supposed to do it in?
Sure. I mean, it would be awesome if we had better observations, but in some sense, we sort of have to work with what we've got, right? We want to solve the problem, and we want to try to make progress on the problem now because that will make it easier to solve in the future. We have some things that we know, and we have some observations. We're not totally naive. And so we can start to make understanding. We can start to produce theoretical models, try to understand what's going on before we get concrete observations. And for some of these things, we might never get concrete observations. So until potentially it's too late. If you think about deceptive alignment, there are scenarios where we don't see. If a deceptive model is good at being deceptive, then we won't learn about the deception until the point at which we deployed it everywhere and it's able to sort of break free of whatever sort of mechanisms we have are sort of doing feedback. And so if we're in a situation like that, you have to solve the problem before you get the observation if you want to not die to the problem. And so it's sort of one of the things that makes it a difficult problem is that we don't get to sort of just rely on these sort of more natural feedback loops of like, when we look at the problem that's happening, we try to come up with some solution and then we deploy that solution because we might not get great evidence, we might not get good observations of what's happening before we have to solve it. And that's sort of one of the things that makes the problem so scary, I think, from my perspective, is that we don't get to rely on a lot of our sort of more standard approaches.
Okay, so on that note, if listeners are interested in following your work, seeing what you get up to, what you're doing in the future, how should they do that?
Yeah, so my work is public, and it's on, basically all of it is on the alignment forum. So you can find me, I am evhub, EVHEB, on the alignment forum. So if you go there, you should be able to just like Google that and find me, or just Google my name. And you can sort of go through all of the sort of different posts and writing that I have. Some good starting points. So once if you've already read risk and optimization, other sort of good places to sort of look at some of the other work that I've done might be an overview of 11 proposals for building safe advanced AI, which I mentioned previously, and goes into a lot of different approaches for like trying to address the like overall AI safety problem, and includes an analysis of all of those approaches on outer alignment and inner alignment. And so trying to sort of understand how would they address base optimization problems and all of this stuff. So I think that's a good place to sort of go in terms of trying to understand my work. There's also another post that might be good would be the relaxed adversarial training for inner alignment post, which I mentioned sort of tries to address the sort of very specific problem of relaxed adversarial training. It's also worth mentioning that if you like risk and optimization, I'm only one of multiple co-authors on the paper, and so you might also be interested in some of the work of some of the other co-authors. So I mentioned that Vladimir McCulloch has a post on suitably robustness, which I think is really relevant, worth taking a look at. I also mentioned some of Yuar's recent stuff on Yuar Skulls on trying to understand some of what's going on with inductive biases and sort of the prior of neural networks. And so there's lots of good stuff there to take a look at from all of us.
Okay, well, thanks for appearing on the podcast, and to the listeners, I hope you join us again. This episode was edited by Finan Adamson.